Look up at the night sky. What do you see? Pinpricks of light, distant suns, the gentle arc of our own galaxy stretching overhead. It feels familiar, almost comforting in its constancy. But that view is an illusion, a tiny glimpse into a reality so vast and strange it defies human comprehension. We are surrounded by mysteries on a scale so grand that even our most brilliant minds can only scratch the surface. For all we've learned about planets, stars, and galaxies, the cosmos holds secrets that remain stubbornly, thrillingly out of reach. These aren't just small gaps in knowledge. These are profound puzzles that challenge the very foundations of what we think we know about reality itself. Today, we're setting out on a journey to explore 25 of the most baffling unsolved mysteries in the cosmos. From the true nature of dark matter and dark energy, invisible forces shaping the fate of the universe, to the eerie silence in our search for extraterrestrial life, each mystery pulls us deeper into the wonder and humility of cosmic exploration. We'll confront questions that have lingered for decades, even centuries. What happens inside a black hole? Are we alone in the universe? Why does the cosmos appear fine-tuned for life? These are not abstract ideas reserved for astronomers in observatories. They speak to something fundamental in all of us, the desire to understand our place in something bigger. So whether you're an avid stargazer or someone who simply enjoys a good mystery, you're invited to join this adventure. Together, we'll navigate through enigmas that defy explanation, marvel at discoveries that rewrite the rules of physics, and maybe, just maybe, catch a glimpse of how much wonder still awaits us in the great unknown. The universe is full of stories waiting to be told, and this is only the beginning. Our journey into the cosmos's greatest puzzles begins not with a distant galaxy, but right here at home, with a question so simple a child could ask it, yet so profound it has haunted scientists for generations. If the universe is so unimaginably vast and ancient, with billions of planets that could support life, then where is everybody? This is the heart of the Fermi Paradox, named for the physicist Enrico Fermi, who, over a casual lunch in 1950, reportedly looked up and asked that very thing. The numbers are overwhelmingly on the side of life. Our Milky Way alone contains an estimated 100 billion stars. Many of those are sun-like, and a significant fraction of those are likely orbited by rocky planets within the habitable zone, that Goldilocks region where water can flow as a liquid. With so many potential incubators for life, and with the galaxy being over 13 billion years old, there has been more than enough time for intelligent civilizations to arise, spread, and make their presence known across the stellar expanse. The silence we hear, then, is deafening. Our radio telescopes scan the heavens, picking up the faint whispers of neutron stars and the residual echo of the Big Bang, but never a deliberate, structured signal from another mind. Our sky remains stubbornly, mysteriously quiet. To frame this immense possibility, scientists use a powerful tool called the Drake equation. It's not so much a formula with a single answer, but a way to break down the enormous question of alien life into more manageable probabilities. It multiplies factors like the rate of star formation, the fraction of stars with planets, the number of habitable planets per system, the odds that life actually emerges on those worlds, the probability that life becomes intelligent and technologically advanced, and finally, the length of time such a civilization might last and broadcast detectable signals into space. Plug in optimistic numbers and the galaxy could be teeming with thousands of communicative civilizations. Use more conservative estimates and the number might drop to a handful or even just one, us. The equation beautifully illustrates the spectrum of possibility, but it doesn't resolve the paradox, it only sharpens it. This glaring contradiction between high probability and zero evidence has led to a fascinating array of proposed solutions. Perhaps the most sobering is the Great Filter hypothesis. This theory suggests that at some point between the emergence of non-living matter and a civilization capable of colonizing stars, there exists an evolutionary or technological barrier that is extremely difficult or perhaps even impossible to surpass. The Great Filter could lie in our past, maybe the jump from simple prokaryotic cells to complex eukaryotic life. An event that took over 1 billion years on Earth is so astronomically rare that it effectively isolates every potential life-bearing world in a primitive state. Or the filter could be waiting for us in our future. It's a chilling thought that the development of advanced technology, like artificial intelligence or nuclear weaponry, might inevitably lead to a civilization's self-destruction, silencing them before they ever get a chance to say hello. Every ancient, silent world we discover that once had the conditions for life adds weight to this ominous possibility. Other explanations are less apocalyptic but equally mind-bending. Maybe spacefaring civilizations are out there, but they're so advanced that our technology is primitive by comparison, like trying to spot a jetliner with a Stone Age telescope. Their methods of communication could be so far beyond our understanding of physics that their signals are all around us, and we simply lack the senses to perceive them. Or consider the zoo hypothesis, the idea that Earth is being deliberately left alone, a sort of cosmic wildlife preserve observed from a distance by galactic sociologists who adhere to a strict policy of non-interference. There's also the possibility that the universe is just too big. The vast distances between stars could be the ultimate prison, making travel or even meaningful communication across the gulfs of space utterly impractical, leaving every civilization an isolated island in a silent sea. The implications of the Fermi Paradox extend far beyond astronomy. They force us to look in the mirror. If the Great Filter is behind us, we are miraculous. We are the winners of a cosmic lottery so rare that we might truly be alone, or at least among the very first. This is a thought that fills one with a profound sense of wonder and responsibility. But if the filter is ahead of us, then every step we take into the future, every technological leap, every global challenge we navigate carries the weight of a test that countless others may have failed. It transforms human history from a mere chronicle of events into a high-stakes drama with consequences on a galactic scale. Our continued survival becomes the most important experiment in the known universe. This paradox holds a mirror to humanity, showing us both our incredible rarity and our profound fragility, a dual truth that makes our search for answers among the stars the most important quest we could ever undertake. Yet for all its dominance, this mysterious substance has never been directly seen or touched. It does not absorb, reflect, or emit any form of light or energy. It is completely and utterly dark. Its presence is known only by the ghostly hand of its gravity, a force that tugs on the visible universe from the shadows. The first compelling evidence for this invisible scaffold came from the careful study of how galaxies spin. In the 1930s, a pioneering astronomer named Fritz Zwicky was observing the Coma cluster, a vast collection of galaxies, and noticed something bizarre. The individual galaxies were moving so fast that the gravity from all their visible stars should not have been nearly strong enough to hold the cluster together. By all rights, the entire system should have flown apart. Zwicky proposed the existence of what he called dunkel materie, or dark matter, an unseen mass providing the extra gravitational glue. Decades later, astronomer Vera Rubin provided even stronger proof by charting the rotation speeds of stars within individual spiral galaxies. According to the laws of gravity established by Newton and Einstein, stars on the outer edges of a galaxy, far from the bright central bulge, should orbit much more slowly, just as Pluto, far from the Sun, moves much slower than Mercury. But Rubin's observations revealed a stunning truth. Stars at the edge of a galaxy orbit just as fast as those near the center. The only explanation is that each galaxy is enveloped in a massive, spherical halo of something invisible, whose gravity is pulling on those outer stars, whipping them around at impossible speeds. Further proof comes from a phenomenon that would have fascinated Einstein himself: gravitational lensing. His theory of general relativity tells us that massive objects warp the fabric of spacetime, bending the path of light that travels past them. This means a massive object, like a galaxy cluster, can act as a cosmic lens, magnifying and distorting the images of more distant galaxies behind it. When astronomers use this technique to map the mass of these clusters, they find that the amount of mass required to create the observed warping is far greater than the mass of all the visible stars and gas put together. The lens reveals a hidden landscape of dark matter, its gravitational influence sculpting the light from the distant universe. So what is it? The leading theory points to entirely new kinds of subatomic particles that rarely, if ever, interact with normal matter through any force except gravity. The prime candidates are known as WIMP, or weakly interacting massive particles. These hypothetical particles would be heavy, slow-moving, and would only interact with the familiar matter of our world through the weak nuclear force, making them incredibly difficult to catch. For decades, scientists have been trying to detect these elusive particles using incredibly sensitive experiments located deep underground, in abandoned mines or tunnels, where they are shielded from the constant rain of cosmic radiation that would overwhelm their delicate sensors. They wait, hoping that on very rare occasions, a WIMP from the vast halo surrounding our galaxy might just bump into the nucleus of an atom in their detector, creating a telltale signal. So far, the detectors have remained silent. Another compelling candidate is the action, a particle originally proposed to solve a different puzzle in particle physics. Actions would be extremely light, almost ghost-like particles that could flood the universe. While they would be even harder to detect than WIMP, their conversion into photons in the presence of strong magnetic fields might provide a way to find them, and experiments are underway to do just that. The world's most powerful particle smasher, the Large Hadron Collider, is also on the hunt. Physicists there are attempting to create dark matter particles by smashing normal particles together at nearly the speed of light, hoping to see missing energy in their collisions that could have been carried away by an invisible particle. The enduring mystery of dark matter is a humbling reminder that the stuff we see, the planets, the stars, even our own bodies, makes up less than 5% of the cosmos. We are a mere afterthought in a universe dominated by a shadow we cannot see, a mystery that continues to challenge our most fundamental understanding of physics and our place in the grand scheme of things. If the gravitational grip of dark matter is the cosmic glue holding galaxies together, then dark energy is its polar opposite, a mysterious, repulsive force acting on the largest scales imaginable, tearing the very fabric of the universe apart. This discovery was so shocking and counterintuitive that it earned the team of astronomers who found it the Nobel Prize in Physics in 2011. For much of the 20th century, scientists were locked in a debate about the ultimate fate of the cosmos. Would the collective gravity of all matter eventually halt the universe's expansion from the Big Bang and pull everything back together in a big crunch? Or would the expansion simply continue to slow down over trillions of years, forever approaching a standstill? The answer, it turned out, was something no one had seriously considered. The expansion isn't slowing down at all. It's speeding up. This monumental discovery was made by two independent teams studying a very specific kind of stellar explosion, a Type 1a supernova. These cosmic blasts are crucial because they are standard candles. A white dwarf star stealing matter from a companion will always explode at almost exactly the same point, when its mass reaches about 1.5 times that of our Sun. This means every Type 1a supernova has nearly the same intrinsic brightness. By measuring how bright they appear to us from Earth, astronomers can calculate a precise distance to these explosions. Furthermore, by analyzing the light from these supernova, they can determine how much the universe has stretched since the moment the light was emitted, telling us how fast the universe was expanding at different points in the past. When both teams compared distant supernovae, those that exploded billions of years ago, to closer, more recent ones, they made a startling discovery. The distant supernovae were dimmer than expected. This meant they were farther away than the standard model of a slowing expansion predicted. The only possible explanation was that the expansion of the universe was not decelerating under gravity's pull, but was instead accelerating, pushed by some unknown repulsive energy. The universe, against all odds, was blowing itself up faster and faster. This mysterious culprit was dubbed dark energy. In the equations of Einstein's theory of general relativity, the most natural place to put an energy that permeates the vacuum of space itself is through the cosmological constant, represented by the Greek letter lambda. Einstein had originally introduced this constant as a fudge factor to force his equations to describe a static, unchanging universe, which was the prevailing belief at the time. When Edwin Hubble later discovered the universe was actually expanding, Einstein reportedly called the cosmological constant his greatest blunder. The irony is profound. His so-called blunder may be the most important term in all of cosmology. The cosmological constant represents a fixed energy density inherent to the vacuum of space. As the universe expands and more space comes into existence, more of this repulsive energy appears, causing the expansion to accelerate. The problem, however, is one of catastrophic proportions. When quantum physicists try to calculate the theoretical value of this vacuum energy, their prediction is off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. It is arguably the worst prediction in the entire history of physics. This cosmological constant problem is a glaring sign that we are missing something fundamental in our understanding, a deep disconnect between the world of the very small described by quantum mechanics and the world of the very large described by general relativity. Not all scientists are convinced the cosmological constant is the final answer. Competing theories suggest that dark energy might not be constant at all. Perhaps it is a dynamic field nicknamed quintessence after the classical fifth element that changes in strength over time. This would mean the acceleration of the universe could vary, potentially increasing even more dramatically in the future or perhaps even fading away. Other, more radical ideas propose that Einstein's theory of gravity itself is incomplete and needs to be modified on the largest cosmic scales to account for what we see, meaning dark energy might not be an energy at all but a sign that our understanding of gravity is wrong. The true nature of dark energy is one of the most pressing questions in all of science because its properties will dictate the ultimate fate of everything. A constant cosmological constant points toward a future where the universe continues to accelerate, eventually tearing apart all galactic structures, leaving islands of stars isolated in an ever-cooling, expanding void. A more vicious form of dark energy could lead to a big rip, where the acceleration becomes so powerful that it shreds galaxies, solar systems, planets, and even atoms themselves apart in a final, violent end. This invisible force, making up about 68% of the universe, is quietly conducting the cosmic symphony, and we are only just beginning to hear its unsettling tune. While dark energy pushes the universe apart on the grandest scales, a more localized yet equally powerful gravitational force is pulling us through the cosmos on a breathtaking journey. Our Milky Way galaxy is not sitting still. It is racing through space at a staggering speed of over 1 million miles per hour, but this isn't a random drift. For decades, astronomers have known that our entire galactic neighborhood, a collection of galaxies known as the local group, is being pulled relentlessly toward a specific point in the sky, toward a mysterious and immense gravitational anchor they call the Great Attractor. Picture our cosmic situation like a leaf caught in a vast, invisible river current, flowing toward a massive waterfall we cannot yet see. This unknown source of gravity must be colossal, with a mass equivalent to tens of thousands of Milky Ways, to exert such a profound influence on us and thousands of other galaxies across a region hundreds of millions of light-years wide? The frustrating challenge in solving this mystery lies in its location. The direction of this pull points toward the constellation Centaurus, a region that, from our vantage point on Earth, is directly behind the plane of our own Milky Way galaxy. This area is nicknamed the Zone of Avoidance. It's not that there's nothing there, it's that our view is completely blocked by the thick clouds of gas and dust and the dense swarms of stars that make up the central bulge of our galaxy. It's like trying to see a distant city from inside a deep fog bank. For a long time, traditional optical telescopes were useless, leaving this enormous section of the universe a blank spot on our maps and the nature of the Great Attractor a matter of pure speculation. The key to peering through this cosmic veil was to use eyes that see a different kind of light. Radio, infrared, and X-ray telescopes can pierce through the obscuring dust, revealing the hidden universe beyond. Pioneering surveys, like those conducted with the Parkes Radio Telescope in Australia, began to meticulously map the thousands of previously unknown galaxies hiding in the zone of avoidance. This painstaking work began to reveal the true source of the immense pull. It wasn't a single, monstrously dense object, but rather an overwhelming concentration of mass, a gigantic supercluster of galaxies. This discovery shifted our understanding from a singular attractor to a vast gravitational watershed. This new map of our cosmic neighborhood led to a breathtaking realization, one that completely redefined our address in the universe. The Great Attractor is not the final destination, but is itself just a part of something exponentially larger. We now understand that our local group, the Great Attractor, and countless other galaxy clusters are all gravitationally bound, flowing together toward a common center of mass. This immense structure, containing over 100,000 galaxies spread across 500 million light-years, has been given the beautiful Hawaiian name Laniakea, which means immeasurable heaven. We reside on the far outskirts of this supercluster, our motion dictated by the gravitational landscape of this colossal cosmic continent. The pull we feel is the combined gravity of Laniakea's core, a dense region dominated by a massive cluster known as the Norma cluster. Yet the story may reach even further. There are hints that the entire Laniakea supercluster might itself be influenced by an even larger gravitational anomaly, a potential supercluster sometimes referred to as the Shapley Attractor, located hundreds of millions of light-years beyond. This reveals a universe structured on scales so vast they are difficult to comprehend, a cosmic web of filaments and nodes where galaxies are mere specks, flowing along rivers of dark matter toward the densest gravitational basins. The mystery of the Great Attractor has evolved from searching for a single hidden monster to understanding our place within an immeasurable heaven, a reminder that we are but a small part of an endless gravitational dance. From the immense gravitational currents of Laniakea, we now turn to a cosmic phenomenon that is not a slow, persistent pull, but a sudden, violent flash, a burst of energy so intense and so brief that for years many astronomers wondered if they were even real. Imagine a single, brilliant flash of radio light traveling across the universe for billions of years. In less time than it takes to blink, this flash releases more energy than our sun puts out over several days. Then it's gone. These are fast radio bursts, or FRB, and they represent one of the most electrifying and perplexing mysteries in modern astronomy. The story of FRBs begins not with a triumphant discovery, but with a piece of data that was almost thrown away. In 2007, a young astronomer named Duncan Lorimer was sifting through archival recordings from the Parkes Radio Telescope in Australia, data that had been collected 6 years earlier while searching for pulsars. Buried in the noise was a signal so powerful and so short it stood out like a scream in a library. It lasted a mere 5 milliseconds. At first, many in the scientific community were deeply skeptical. Could it have been a glitch from Earth, a malfunctioning microwave oven in the observatory kitchen, or perhaps a satellite passing overhead. But as years went by, more of these bursts were found by other telescopes around the world, confirming they were indeed real and coming from deep space. They were not local, they were extragalactic, originating from galaxies far beyond our own. This opened up a Pandora's box of questions, the most pressing being, what in the universe could possibly create such a spectacular, short-lived event? The hunt was on to find more of them and, crucially, to figure out where they were coming from. Early on, a major breakthrough came with the realization that not all FRBs are created equal. The vast majority appear to be one-off events, a single catastrophic explosion that never repeats, but a small fraction of them do something even more bizarre: they repeat. They flash once, then go silent for a while, only to flash again and again from the exact same spot in the sky. This distinction between repeating and non-repeating bursts immediately suggested that there might be at least two different kinds of cosmic engines powering these incredible flashes. For the non-repeating bursts, the best explanation points to a single cataclysmic event. The prime suspect is the merger of incredibly dense stellar remnants, like two neutron stars colliding or a neutron star being consumed by a black hole. Such an event would release a titanic amount of energy in a final, violent moment, perfectly matching the profile of a one-time, only FRB. The repeating bursts, however, require a source that can survive its own outburst. It needs to be an object that can have multiple tantrums. Here, the evidence has increasingly pointed toward a specific type of neutron star known as a magnetar. Neutron stars are the collapsed cores of massive stars, and magnetars are a special variety with magnetic fields so unimaginably powerful they are the strongest magnets in the universe. A magnetar's crust is under immense strain from these fields, and theorists propose that a starquake, a sudden cracking of the star's rigid surface, could unleash a tremendous shockwave, accelerating particles and creating a blast of radio waves that we see as a repeating FRB. In a stunning piece of detective work in 2020, astronomers actually observed a magnetar within our own galaxy producing a burst that had all the hallmarks of a much weaker FRB, providing the first direct evidence linking at least some of these events to these cosmic powerhouses. Of course, anytime there's a mysterious signal from deep space, the question of extraterrestrial intelligence arises, and FRBs are no exception. The precision and power of these bursts led some, including renowned astrophysicist Avi Loeb, to cautiously speculate that they could potentially be evidence of advanced technology. Perhaps they are powerful beams from interstellar light sails, used to propel spacecraft across the galaxy, and we are simply seeing the leakage of that energy as the beam sweeps across our line of sight. While this is considered a less likely possibility by most scientists, it highlights just how extraordinary these signals are. They push us to consider every explanation, from the known extremes of physics to the truly unknown. The real revolution in solving this mystery, however, is coming from a new generation of telescopes that are turning detection into a regular event. Facilities like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, are now discovering hundreds of new FRBs. Its design allows it to stare at a huge swath of sky every day, making it a perfect FRB finding machine. But the true key to unlocking their secrets has been the ability to pinpoint their exact origins. When a radio wave travels through the vast clouds of ionized gas that drift between galaxies, different frequencies of the wave travel at slightly different speeds. This causes the burst to spread out, with higher frequencies arriving at our telescopes a fraction of a second before the lower ones. By measuring this spread or dispersion, astronomers can estimate how much material the signal has traveled through, giving them a rough distance. To get a precise location, however, requires a different technique. Using arrays of radio dishes spread across a continent, like the Very Large Array in New Mexico or the Australian Square Kilometre Array Pathfinder, scientists can use the tiny differences in the arrival time of the signal at each dish to triangulate the FRB's origin with incredible precision, often pinpointing it to a specific host galaxy billions of light years away. This is more than just cosmic cartography. It's a powerful new tool for exploring the universe itself, because these bursts act like a flashlight beam shining through the cosmic fog. They illuminate the otherwise invisible material that exists in the space between galaxies. By analyzing how the FRB's signal has been distorted and delayed on its journey, astronomers can literally weigh the missing ordinary matter in the universe, helping to solve another long-standing mystery. Each new burst is not just a puzzle to be solved, but a probe sent to us from the distant cosmos, carrying encoded information about the vast, empty spaces it has traversed. They are fleeting, enigmatic, and incredibly powerful, reminding us that the universe is still full of surprises that can arrive in a flash. Amidst the chaotic and fleeting crackle of fast radio bursts, there exists a signal from the cosmos that is notable not for its power or repetition, but for its profound and enduring silence. It was a whisper so perfectly tuned, so seemingly deliberate, that it has become the most famous and frustrating anomaly in the entire history of the search for extraterrestrial intelligence. It is known simply and perfectly as the WOW signal. The story begins on a warm summer evening in Ohio, August 15, 1977. The Big Ear Radio Telescope, a massive stationary array operated by Ohio State University, was dutifully scanning the sky as part of the SETI project, listening for any sign of an artificial broadcast from the stars. Its method was systematic but slow. It would stare at a fixed point in the sky as the Earth's rotation swept its field of view across the cosmos. That night, just after 11:16, something extraordinary happened. For 72 glorious seconds, the telescope's receiver was flooded with an intense, uninterrupted radio signal. It was a narrowband signal, meaning it was concentrated on one very specific frequency, just like a terrestrial radio station. This is crucial because natural cosmic objects like stars or nebulae emit radio waves spread across a wide range of frequencies. A narrowband signal is the hallmark of an engineered transmitter. The data from the telescope was printed out on line after line of alphanumeric characters representing signal intensity. A few days later, a young volunteer astronomer named Jerry Amon was sifting through the reams of computer printouts when he saw it. On the page, the sequence of characters for that particular time read 6EQUJ5. The numbers and letters corresponded to the signal's strength. The normal background noise of space registered as a 1 or a 2. This sequence shot off the chart. Stunned, Amon circled the characters in red pen and in the margin wrote a single heartfelt word that would immortalize the event: WOW. The name stuck. The signal's intensity had a unique shape, rising and then falling over the 72-second window, exactly matching what astronomers would expect from a steady, distant source passing through the fixed beam of the Big Ear telescope. It was a perfect candidate, but what made this signal so tantalizing wasn't just its strength, it was the frequency it used. The WOW signal was detected at 1,420 MHz. To a radio astronomer, that number is anything but random. It is the emission frequency of the hydrogen atom, the most common element in the universe. Hydrogen is the basic building block of everything, and the logic behind using its frequency is brilliant in its simplicity. Any technologically advanced civilization looking to announce its presence would likely recognize this frequency as a universal standard, a natural lighthouse beacon around which to build a channel for communication. It is the cosmic equivalent of tuning to the most popular radio station in the galaxy. The signal appeared to originate from the direction of the constellation Sagittarius, in a region devoid of any known stars or planets at the time. It had all the markings of a deliberate hello, and then it vanished. The most agonizing part of the WOW signal mystery is that it was never heard again. Despite decades of dedicated searches by more powerful telescopes like the Very Large Array and countless hours of pointed observations toward that same patch of sky, the silence has been absolute. This one-off nature is the primary reason it remains an enigma. If it was a deliberate broadcast from an alien civilization, why only once? One theory suggests it could have been a targeted beam, a brief, focused message aimed deliberately at us that simply moved on. Perhaps it was an omnidirectional beacon that we happened to drift through, catching just a fleeting moment of its continuous transmission. Or maybe the source was destroyed or ceased broadcasting shortly after we heard it. The possibilities are as endless as they are untestable. The lack of a repeat performance has also fueled the search for a natural explanation, something that could mimic an artificial signal. For years, all proposed natural causes fell short. It couldn't have been a satellite or aircraft, as those move quickly and would have been tracked. It wasn't random radio interference from Earth, as the Big Ear used two separate feed horns that listened to the sky just minutes apart. A local signal would have appeared in both, but the WOW signal was only detected in one. For decades, it seemed to stand alone, defiantly unexplained. Then, in 2016, a new hypothesis emerged that reignited the debate. Professor Antonio Paris of St. Petersburg College proposed that the signal could have been caused by a cloud of hydrogen surrounding a comet. Two comets, named 266P/Christensen and 335P/Gibbs, were in the exact area of the sky the Big Ear was scanning on that August night, and they were not known to astronomy in 1977. The idea is that the vast clouds of hydrogen gas that surround comets could, under the right conditions, emit a narrowband radio signal at that magic frequency. This offered a potential mundane solution to a 40-year-old mystery. However, the comet hypothesis has been met with significant skepticism within the astronomical community. Critics point out that cometary hydrogen clouds are diffuse and are not known to produce such an intense, short-duration, and isolated burst of radio waves. Subsequent analysis has suggested the emission would likely be far too weak to account for the powerful signal that was recorded. The debate continues, a testament to the signal's enduring power to captivate and confound. The WOW signal sits in a unique category. It is not confirmed as a sign of life, yet no natural explanation has been universally accepted. It is a single data point, a one-in-a-lifetime event that serves as both the best example of what we might hope to find and a sobering lesson in the immense difficulty of this search. It is a ghost that visited us once, a perfect cosmic shout that became the most eloquent silence, reminding us that the universe is quite capable of keeping its secrets, even when it seems to be whispering them directly in our ear. While the WOW signal remains a singular, unexplained event, our next cosmic conundrum involves a star that has been behaving bizarrely for years, its light flickering in ways that defy all standard astronomical explanations. This is the story of KIC 8462852, better known as Boyajian star, or more popularly, Tabby's star, named after the astronomer who led its investigation, Tabitha Boyajian. Located about 1,400 light-years away in the constellation Cygnus, this otherwise ordinary star became an internet sensation and a scientific obsession for one simple reason: it wouldn't stop dimming in the strangest ways imaginable. Its discovery is a triumph of modern citizen science. The star was first flagged not by a professional astronomer in an observatory, but by volunteers for the Planet Hunters project, who were sifting through the immense trove of data from NASA Kepler Space Telescope. Kepler's primary mission was to find exoplanets by detecting the telltale, periodic dips in a star's brightness that occur when a planet passes in front of it. These transits are predictable, symmetrical, and typically cause a dimming of less than 1%. What the volunteers found in the data for this star was something entirely different. They observed deep, irregular, and asymmetric dips in its light. Some drops were a slight few percent, but others were catastrophic, with the star's light plummeting by a staggering 22%. These dips had no consistent timing, lasting for days or even weeks at a time, with sudden, sharp drops and gradual, uneven recoveries. This was not the signature of a neat, circular planet. It was the light curve of chaos. The most extraordinary of these dimming events prompted the now famous paper titled, "Where's the Flux?", a playful nod to the mystery, and it immediately set the astronomical world ablaze with speculation. When a star of this age and type dims so dramatically, the immediate natural suspect is dust. A cloud of fine debris, perhaps from a catastrophic collision of planets or asteroids, could unevenly block the star's light. The problem was that even large dust clouds should be transparent to infrared light, but observations showed the dimming was consistent across wavelengths, which is not typical for simple dust. This inconsistency is what opened the door to more exotic ideas. The most captivating and widely publicized theory came from astronomer Jason Wright, who suggested the pattern was consistent with a vast, partially completed alien megastructure, specifically a Dyson swarm. The concept, proposed by physicist Freeman Dyson, imagines an advanced civilization harnessing the entire energy output of its star by constructing a colossal array of energy-collecting satellites or panels orbiting it. Such a structure would indeed block light in an irregular, non-periodic way, exactly as observed. While Wright and others were clear this was an absolute last resort hypothesis, the idea of possibly seeing the handiwork of an alien civilization was too thrilling to ignore. This launched Tabby's star into the scientific and cultural spotlight, becoming one of the most intensely monitored stars in the sky. A subsequent Kickstarter campaign raised over $100,000 to secure dedicated time on global networks of telescopes, allowing for around-the-clock observation. This massive effort has, over time, begun to paint a clearer, though no less fascinating, picture. Extensive monitoring has revealed that the star isn't just experiencing sudden, deep dips, it is also undergoing a long-term secular dimming. Over the century-long span of historical photographic plate data from Harvard Observatory and confirmed by Kepler's 4-year mission, the overall brightness of Tabby's star appears to have gradually faded by a significant amount. This combination of short-term chaotic dipping and long-term fading made a simple dust cloud theory seem inadequate, but it also made a solid, alien megastructure seem even less likely. The breakthrough in the mystery came from detailed spectroscopic observations during a major dimming event. By carefully analyzing the star's light as it faded, astronomers could determine what was blocking it. The key finding was that the dimming was more pronounced in blue light than in red light. This is the definitive fingerprint of dust. Small dust particles scatter blue light more effectively than red light, which is why our sun looks red at sunset. The blue light has been scattered away by dust in our atmosphere. This evidence strongly suggests a natural cause, likely a vast, uneven cloud of fine circumstellar dust, possibly from the breakup of a comet or a family of exocomets on a long, elliptical orbit. The irregular timing of the dips could be explained by the chaotic nature of this swarm passing in front of the star. The long-term fading could be caused by a larger, more dispersed cloud of debris slowly moving into our line of sight. Yet, even with dust as the leading culprit, the mystery is far from completely solved. The central question remains, what event could have created such an immense and peculiar dust cloud in the first place? The star is not young, so it shouldn't have a thick protoplanetary disk of leftover material. A recent planetary collision could be the answer, but that itself is an extraordinarily rare event to witness. Some scientists have proposed that the dust might be trapped and shaped by the gravitational influence of an unseen planet, creating clumps and arcs that orbit the star. Others point to intrinsic stellar activity, suggesting the star itself might be undergoing a period of unprecedented and poorly understood variability, though this doesn't easily account for the extreme, discrete dips. Tabby's star endures as a powerful reminder that nature is often more creative than our wildest science fiction. It taught us the value of public engagement in science and showed that our telescopes can reveal anomalies we never thought to look for. It may not be aliens, but it is undoubtedly something strange, a cosmic puzzle that continues to challenge our understanding of how solar systems evolve and what kind of chaos can unfold around a distant sun. While we search for answers in the flickering of distant stars, some of the most baffling cosmic mysteries have been discovered much closer to home, not by watching the heavens, but by tracking the precise trajectories of our own robotic explorers as they voyage into the deep. For decades, two pioneering spacecraft presented scientists with a persistent and tiny mathematical riddle, a deviation so small it was almost dismissed, yet so stubborn it refused to go away. This is the story of the Pioneer Anomaly. In the early 1970s, humanity launched its first emissaries destined to leave our solar system. Pioneer 10 and Pioneer 11 were marvels of engineering, tasked with the first ever flybys of Jupiter and Saturn before embarking on a one-way trip into the interstellar void. For years, they faithfully phoned home, their weak radio signals tracked with exquisite precision by NASA, a deep space network. By carefully measuring the Doppler shift in these signals, the tiny change in frequency caused by the spacecraft's motion, navigators could calculate their position and velocity to an accuracy of millimeters per second. It was within this incredibly precise data that a subtle ghost appeared. As the twin probes journeyed beyond the orbit of Saturn, engineers noticed something was ever so slightly wrong. Both spacecraft were experiencing a constant sunward deceleration. They were slowing down by a minuscule amount, about 8.74 times 10 to the minus 10 meters per second squared, as if an invisible, gentle hand was applying a tiny brake, pulling them back toward the inner solar system. This was not part of the plan. The gravitational pull of every known object from the Sun and planets to the asteroid belt had been meticulously accounted for in the complex orbital models. Yet, this anomalous acceleration remained, a persistent drift that accumulated over years into a significant navigational discrepancy. By the time Pioneer 10 was more than 7 billion miles from Earth, it was over 240,000 miles off its predicted course. For a community of scientists and engineers who pride themselves on being able to plot a course to a specific moon of Jupiter years in advance, this was deeply unsettling. It suggested a fundamental flaw in our understanding of gravity itself on the largest scales. The implications were profound, immediately sparking a decades-long investigation. Could this be the first hint of a failure in Einstein's theory of general relativity? Perhaps gravity behaved differently at the extreme distances of the outer solar system. Some theorists proposed exotic new physics, including the influence of unseen dark matter in a halo around our Sun, or modifications to the laws of gravity that would only become apparent in the weak field regime far from the Sun's strong pull. The most tantalizing idea was that we were seeing the first evidence of a cosmological influence within our own solar system, a tiny, local manifestation of the same dark energy that was accelerating the expansion of the entire universe. The mystery captivated physicists and astronomers for over 20 years, a testament to how even the smallest inconsistency can challenge our most fundamental models of reality. The painstaking work to solve the puzzle fell to a tireless team led by physicist Slava Turyshev. He tracked down decades of old data stored on magnetic tapes and even older printouts, often held by retired engineers, and led a heroic effort to digitize and reanalyze this historical record. The key to cracking the case, it turned out, was not in the void of space, but in the mundane details of engineering and thermodynamics. The Pioneer spacecraft were powered by radioisotope thermoelectric generators, or RTG. These nuclear batteries produced heat as a byproduct which was then converted into electricity. The team began to ask a critical question: what happened to all that waste heat? Through meticulous modeling, they realized the answer had been in plain sight all along. The heat emitted by the RTGs and the onboard electronics was being radiated away from the spacecraft. However, the asymmetric design of the probes meant this radiation wasn't perfectly even. More heat was reflected off the large, parabolic high-gain antenna dish on the front of the craft than from the back. This created a tiny but very real photon thrust, a recoil force from the photons of heat themselves pushing back on the spacecraft. It was a real-world demonstration of Einstein's most famous equation: energy has mass, and the emission of that energy produces a force. When the team finally completed their complex thermal model, the results were stunning. The calculated force from this anisotropic heat radiation almost exactly accounted for the mysterious acceleration. The Pioneer Anomaly had a mundane, mechanical explanation. It wasn't new physics, it was old physics applied with a new level of detail to a complex system. The announcement in 2012 was met with a mix of triumph and slight disappointment. A great mystery had been solved, closing a chapter on one of space science's most enduring puzzles. Yet, for the most keen observers, a tiny sliver of the anomaly remained. Even after accounting for the thermal effect, a minuscule residual acceleration, a small fraction of the original signal, seemed to persist in the data. Was this merely an artifact of the incredible complexity of the modeling, an uncertainty that could never be fully eliminated? Or could it be a whisper of something else, a truly new physical effect waiting to be discovered by a future, even more precise, deep space mission? The story of the Pioneer Anomaly is a masterclass in scientific diligence, a reminder that the universe often hides its secrets not in grand gestures, but in the whisper-quiet details of a data stream, and that the most satisfying answers often come from looking not out at the cosmos, but closely and carefully at the machines we send to explore it. Moving from the precise navigation of our own spacecraft to the very formation of our closest celestial companion, we arrive at a mystery that strikes at the heart of our own planet's history. The origin of Earth's moon seems like it should be a settled question. We've been there, we've walked on its surface, and we've brought back hundreds of pounds of its rock. Yet, the more we study those samples, the more the moon's serene presence in our night sky becomes a profound puzzle. How did it get there? The answer is far from simple, and the leading theory, while elegant, is now facing its own set of challenges born from the very evidence it once seemed to explain. For much of the 20th century, astronomers wrestled with three main ideas. The capture theory proposed that the moon was a wandering planetary body, captured whole by Earth's gravity as it drifted through the early solar system. While this would explain the moon's size, the mechanics of such a gentle capture are incredibly difficult to model. It's far more likely a passing object would either crash into Earth or be slingshotted away. The fission theory suggested that the early, rapidly spinning Earth flung off a blob of molten material that coalesced into the moon. This was an appealing idea, as it would naturally explain why the moon orbits in the same plane as Earth's equator. However, it requires an initial spin for our planet that would have been impossibly fast, and it offers no clear reason for the subtle chemical differences we now know exist. Finally, the co-accretion theory posited that Earth and the Moon formed side by side as a double planet from the same primordial cloud of dust and gas. This, too, struggled to account for the Moon's specific composition and its large size relative to Earth, a ratio unlike any other planet-moon system in the inner solar system. The solution that eventually swept the field is both violent and beautiful: the giant impact hypothesis. Picture the solar system in its infancy, over 4.5 billion years ago, a chaotic and violent construction zone. A newly formed proto-Earth, still molten from its own violent assembly, shares its orbit with a countless number of other planetary embryos. According to the theory, one of these, a Mars-sized object scientists have named Theia, struck the young Earth in a catastrophic, glancing blow. The impact was not a direct hit, but a sideswipe that would have vaporized Theia and gouged out a massive portion of Earth's mantle, blasting a colossal plume of vaporized rock into orbit around our wounded planet. In the aftermath, this torrid disk of debris, a mixture of material from Theia and the Earth, quickly coalesced through gravity, cooling and accreting to form our moon. This model elegantly solved many problems at once. It explained the moon's large size. It accounted for the moon's iron-poor composition, as the impact would have ejected mantle material from both bodies while their dense iron cores would have merged and sunk into the Earth's center. It also provided a compelling reason for Earth's axial tilt and the moon's initial molten state. For decades, this was the reigning champion, a brilliant narrative that seemed to fit the facts. The proof, it was believed, would be in the chemistry. If the moon formed primarily from the mantle of Theia, then the isotopic fingerprints of lunar rocks, the unique ratios of elements like oxygen, titanium, and tungsten, should be distinctly different from those on Earth. Every planetary body in the solar system has a slightly different isotopic signature, a cosmic DNA that tells scientists where it formed. This is where the mystery deepens. When Apollo astronauts brought moon rocks home, geochemists made a startling discovery. The isotopic ratios of oxygen, titanium, tungsten, and many other elements in lunar samples are virtually identical to those found in Earth's mantle. It's as if the moon and Earth are made from the exact same stock of materials. This was a massive problem for the standard giant impact model. If Theia was a separate planetary embryo that formed in a different part of the solar system, as it almost certainly would have, its isotopic signature should be different. The moon should carry the chemical ghost of this lost planet, but it doesn't. It looks, for all intents and purposes, like it's made almost entirely of Earth. This confounding chemical congruence has forced scientists back to the drawing board, leading to a new generation of more complex and dramatic impact simulations. Perhaps Theia formed very close to Earth in its orbital neighborhood, sharing a similar composition from the start, making it an isotopic twin rather than a stranger. While possible, this requires a very specific and perhaps unlikely set of initial conditions. More recent computer models have explored the possibility of a much more violent impact. What if Theia was far larger or the collision was far more energetic? New simulations suggest a high-energy, high-angular momentum impact could have created a cynosure, a vast donut-shaped mass of vaporized rock that once enveloped both the Earth and the newborn moon. In this incredibly hot and well-mixed environment, the material from Earth and Theia would have been thoroughly churned together before the moon condensed out of the outer edge of the torus. This could explain the isotopic similarity, as the moon would have formed from a homogenized blend of both worlds. Other models propose that the impact was so extreme that it completely vaporized Theia and a large portion of Earth, creating a dense atmospheric ocean of rock vapor that allowed for thorough mixing before the moon began to accrete. The mystery of the moon's birth is a brilliant example of how science works. A good theory emerges, it explains the major observations, and then more precise data reveals new layers of complexity that force the theory to evolve. The giant impact is almost certainly the right framework, but the devil is in the isotopic details. The answer may lie in even more sophisticated computer modeling, or it may require a sample return mission from the moon's far side or its deep mantle to find a piece of rock that somehow preserves a tiny trace signature of the long-vanished Theia. Our moon is not just a dead rock, it is an archive holding the violent record of Earth's earliest history, a time when the solar system was a shooting gallery and a single collision shaped the destiny of our world, making it a habitable planet with stable seasons and tides, and gifting it with a constant companion whose origin story we are still striving to read. Just as we unravel the history of our own moon, the solar system occasionally offers us a visitor from a place far beyond our own neighborhood, a messenger from the interstellar void that challenges our definitions of what an object in space can be. In October 2017, the Pan-STARRS telescope in Hawaii detected a faint point of light moving at breathtaking speed. Its trajectory was immediately and stunningly clear. This was no asteroid from our solar system. It was the first interstellar object ever observed passing through our cosmic backyard. It was given the name Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. And what a strange messenger it proved to be. The initial data revealed an object unlike any we had seen before. Its path was hyperbolic, meaning it was not bound by the sun's gravity. It was a tourist just passing through, entering our system from above the plane of the planets and slingshotting around the sun before hurtling back out into deep space. But the real mysteries began when astronomers tried to pin down its physical characteristics. As it tumbled through space, its brightness varied dramatically by a factor of 10. This extreme change in luminosity pointed to an object with a highly elongated shape, like a cigar or a pancake, with an estimated length perhaps 10 times its width. This was bizarre, as most natural objects in our solar system are far more rounded. Compounding the strangeness was its complete lack of a visible coma, the hazy envelope of gas and dust that surrounds a comet. It showed no outgassing, no tail, appearing for all the world like an inert, rocky asteroid. But then, several weeks after its closest approach to the Sun, another anomaly emerged. Precise tracking revealed Oumuamua was ever so slightly accelerating away from the Sun, deviating from the precise path dictated by gravity alone. Something was giving it an extra push. The scientific community immediately set to work explaining these oddities with natural phenomena. The leading explanation for the acceleration became sublimation. As a comet approaches the Sun, ices on its surface heat up and turn directly to gas, jetting away and providing a small rocket-like thrust. For Oumuamua, it was proposed that its ices were hidden beneath a solid, insulating crust of organic material, and the outgassing occurred in narrow jets that wouldn't produce a widespread, visible coma or dust tail that our telescopes could detect. This could explain the acceleration without violating known physics. The unusual shape, while extreme, could also be a natural product of its long journey through interstellar space, where collisions and tidal forces from distant stars might sculpt such a form over millions of years. Some researchers even suggested it could be a shard of a Pluto-like world shattered by a distant impact, or a fractal-like aggregate of dust known as a dust bunny, whose low density and large surface area could account for both the acceleration and the strange light curve. However, the peculiarities of Oumuamua were so pronounced that they prompted a handful of scientists, most notably Harvard astronomer Avi Loeb, to cautiously propose a more extraordinary hypothesis, that Oumuamua could be a piece of advanced alien technology. The core of the argument rested on the object's unusual acceleration and its apparent shape. The acceleration was smoothly continuous and decreased with distance from the Sun, exactly as one would expect, but it seemed too efficient for a dirty ice ball. Loeb and his colleague calculated that if Oumuamua were a light sail, a thin, reflective sheet designed to be pushed by the radiation pressure from starlight, its dimensions and behavior could be explained. A light sail of the inferred thickness would be incredibly thin, perhaps only a fraction of a millimeter, and could account for the non-gravitational acceleration without needing any visible outgassing. The object's unusual tumbling could then be explained as the chaotic motion of a discarded, derelict sail drifting through space. This was not a claim of a directed alien probe, but rather the possibility that we were looking at a piece of extraterrestrial technological debris, a forgotten artifact from a civilization far away. This idea, while captivating to the public, was met with significant skepticism from the broader scientific community. Critics argued that invoking aliens was the last resort of science, and that extraordinary claims require extraordinary evidence that was, in this case, sorely lacking. The object was only observed for a few weeks, and the data we collected was limited and imperfect. We never got a clear picture of it, Its size, shape, and composition are all inferences based on its brightness and motion. The natural explanation of a water-ice comet with unusual outgassing properties, while not perfect, remains the preferred theory for most astronomers, as it stays within the bounds of known physics. The subsequent discovery of a second interstellar object, the clearly cometary 2I/Borisov, which sported a prominent tail and coma, showed that icy interstellar visitors do exist, making Oumuamua's lack of such features even more puzzling, but not necessarily unnatural. The true legacy of Oumuamua is not that it provided an answer, but that it highlighted a profound question. For the first time, we witnessed an object from another star system, and it was nothing like what we expected. It forced us to acknowledge that the processes of planet and comet formation around other stars may produce objects that are strange and unfamiliar to us. It revealed the limitations of our current observational capabilities. By the time we knew it was there, it was already too faint and too far away to study in detail. This has spurred plans for future missions like the European Space Agency's Comet Interceptor, designed to lie in wait for the next such visitor, ready to launch on short notice for a close-up rendezvous. Oumuamua was a fleeting glimpse, a single blurry frame in a much longer film about the diversity of the galaxy. It remains an enigma, a catalyst for debate that stretches from the hard thermodynamics of outgassing ices to the furthest frontiers of scientific speculation, a silent testament to how much we still have to learn about what else is traveling through the vast darkness between the stars. While the bizarre trajectory of Oumuamua presented a fleeting mystery, a far more persistent and fundamental puzzle has been hiding in plain sight for decades, one that strikes at our most basic inventory of the cosmos. We've already explored the dominance of dark matter and dark energy, the mysterious substances that make up 95% of the universe's mass energy content. But what about the remaining 5%? This is the ordinary matter, the baryonic matter, that makes up everything we can see and touch: stars, planets, gas clouds, and even ourselves. You would think that counting this familiar stuff would be the easy part. Astonishingly, it's not. When cosmologists add up all the ordinary matter they can directly observe in the present-day universe, all the stars in all the galaxies, all the cold gas, all the dust, they come up dramatically short. A staggering 30 to 40% of the ordinary matter that should exist, according to our precise measurements of the early universe, is simply missing. It's a cosmic accounting error on a grand scale, a case of misplaced universal luggage. The evidence for this missing matter comes from two completely independent ways of measuring the universe's contents, and their glaring disagreement is what creates the mystery. The first method looks all the way back to the very beginning, the afterglow of the Big Bang, the cosmic microwave background radiation, is a frozen snapshot of the infant universe when it was only 380,000 years old. By meticulously analyzing the tiny fluctuations in this background hum, scientists can calculate the precise total density of ordinary matter that must have been present at that time. This is our starting inventory. The second method is to take a census of the universe today. We add up the mass locked in stars, the cool hydrogen gas detected by radio telescopes, the hot plasma within galaxy clusters observed by X-ray observatories, and every other form of baryonic matter we can think of. No matter how you slice it, the modern tally only accounts for about 60 to 70% of the original amount. This isn't an exotic substance like dark matter. This is the same protons and neutrons that form the bedrock of reality. They were here at the start, but now, in the contemporary universe, a huge portion of them seem to have vanished without a trace. So, where did it all go? The leading hypothesis points not to some far-flung corner of space, but to the vast, empty voids between galaxies. For years, astronomers suspected that the missing baryons might be hiding in a diffuse, hard-to-detect web of warm gas spread throughout the cosmos. This theoretical structure is known as the warm-hot intergalactic medium, or WIM. Picture the universe not as a collection of isolated galaxies, but as a colossal cosmic web, a spider's silk of dark matter upon which ordinary matter is also arranged. At the intersections of these dark matter filaments, galaxies and massive clusters form. But the spaces between these nodes are not truly empty. They are thought to be filled with incredibly tenuous filaments of gas, heated to temperatures between 10,000 and 10 million degrees Kelvin by the gravitational shock waves from the formation of the large-scale structure of the universe. Gas this hot doesn't behave like the cool hydrogen clouds we're used to finding. It is so ionized its electrons stripped from their atoms that it doesn't emit or absorb light in convenient, recognizable ways. It is, for all intents and purposes, virtually invisible to most of our telescopes. It's the ultimate game of cosmic hide and seek, with the hidden matter making up the very fabric of intergalactic space. How do you find something that is practically invisible? You wait for it to cast a shadow. The strategy astronomers use is as ingenious as it is delicate. They use the brightest beacons in the universe, quasars, as cosmic flashlights. A quasar is the intensely luminous core of a distant galaxy, powered by a voracious supermassive black hole. Its light travels for billions of years to reach us, and on its journey, it passes through these invisible filaments of the WIM. While the hot, ionized gas itself doesn't emit much light, the atoms within it can still absorb very specific wavelengths of light that pass through them. As the quasar's light pierces these filaments, atoms like oxygen and nitrogen, which are highly ionized, imprint incredibly faint absorption lines onto the quasar's spectrum. It's like analyzing a brilliant light after it has passed through a mostly transparent fog. By studying the specific colors of light that are subtly dimmed, you can determine the exact composition and properties of the fog itself. This requires exquisitely sensitive spectroscopy, primarily from space-based telescopes like the Hubble Space Telescope and X-ray observatories, which can detect these subtle fingerprints without the blurring effect of Earth's atmosphere. This painstaking work has recently begun to pay off, turning the WIM from a compelling theory into an observable reality. In recent years, astronomers have successfully identified these telltale absorption lines from highly ionized oxygen in the spectra of numerous quasars, providing the first direct evidence for the missing baryons woven into the cosmic web. The evidence suggests this intergalactic material isn't uniform. It exists in a variety of densities and temperatures, from warmer, more diffuse gas to hotter, slightly denser knots at the intersections of the cosmic filaments. Each detection is like finding a single piece of a massive, universe-spanning puzzle, slowly confirming that the missing matter has been there all along, hidden in the million-degree atmosphere that fills the space between the galaxies. It is crucial to distinguish this missing baryon problem from the mystery of dark matter. They are two entirely different puzzles. Dark matter is a mystery of substance. It is something entirely new, a type of matter that does not interact with light or normal matter except through gravity. The missing baryons, on the other hand, are a mystery of location. We know exactly what this matter is: protons, neutrons, electrons, the same stuff we are made of. The problem is that we couldn't find where it all was hiding in the present-day universe. Solving the missing baryon problem doesn't require new physics. It requires incredibly advanced instrumentation and clever techniques to detect ordinary matter in an extraordinary state. The ongoing hunt for the WIM is a testament to astronomical ingenuity, a relentless effort to complete the inventory of the familiar universe and finally account for every last atom that was present at the dawn of time. But perhaps the most unsettling cosmic anomaly isn't something we're missing, but something we see all too clearly: a pattern in the universe's oldest light that seems to point a mysterious finger directly at us. A finding so potentially paradigm-shattering it has been given the dramatic and foreboding title, the Axis of Evil. To understand why this discovery is so troubling, we need to travel back to the very foundations of modern cosmology, to a pair of principles that are so fundamental they are almost taken for granted. The first is the cosmological principle, which states that on the largest scales, the universe is homogeneous and isotropic. This is a fancy way of saying the universe should look roughly the same in every direction and from every location. There are no special places or preferred directions. There is no center and no edge. The second is the concept of Gaussian or random fluctuations. The seeds of all structure in the universe, the galaxies, clusters, and vast cosmic web are believed to have been planted by tiny, random quantum fluctuations that were magnified to cosmic proportions during a period of rapid inflation just after the Big Bang. Because these fluctuations were random, their imprint on the universe's first light should also be random, without any preferred axis or alignment. The cosmic microwave background radiation is that first light, a snapshot of the universe when it was only 380,000 years old, and it is the ultimate testing ground for these principles. The mystery began to emerge in the early 2000s with the release of exquisite data from NAS, a Wilkinson Microwave Anisotropy Probe, or WMAP. This spacecraft mapped the CMB with unprecedented precision, measuring the tiny temperature variations on the order of 1/100,000th of a degree that correspond to those primordial density fluctuations. As cosmologists pored over the beautiful all-sky map, they noticed something strange. Some of the largest scale patterns in the data, the very low number multipoles, seemed to be aligned with each other in a way that was suspicious. They weren't randomly oriented as expected. Their axes appeared to be coordinated, and what's more, this preferred axis seemed to be eerily aligned with our own solar system's plane of orbit around the Sun, the ecliptic. This was deeply bizarre. Why would the largest scale structure of the entire universe, dating back to its infancy, have any correlation whatsoever with the mundane motion of our tiny, modern-day solar system? It would be like finding that the blueprint for a massive city was secretly aligned with the layout of a single pebble in a suburban garden. The statistical significance of this alignment is what turned a curiosity into a serious concern. When researchers calculated the odds of such an alignment occurring by pure chance in a random, isotropic universe, they found it was less than 1%. Some analyses have even suggested odds as low as 1 in 1,200. In most scientific fields, a 5% chance of being a fluke is considered the threshold for something interesting, so a result with a probability of less than 1% demands attention. This apparent preferred axis, this axis of evil as it was quickly and memorably dubbed, seems to point a line through the universe that somehow involves us. This immediately triggers every scientist's skepticism about a look elsewhere effect or an observational bias. The most obvious and persistent suspicion is that this is not a feature of the universe at all, but an artifact of our own measurement process, an unaccounted for instrumental error or a contamination from within our own cosmic neighborhood. The prime suspect for such local contamination is something called the kinetic quadrupole. Because our solar system is moving relative to the rest frame of the CMB, the light we receive appears slightly warmer in the direction we're heading and slightly cooler in the direction we're leaving. This Doppler shifting effect can create a specific pattern in the data that must be carefully subtracted out to see the true primordial CMB. If this subtraction isn't done perfectly, it could leave behind a residual signal that mimics a large-scale alignment. Other potential culprits include dust in our own solar system, emissions from our own galaxy that weren't fully removed during data processing, or even a subtle gravitational lensing effect that has distorted the primordial signal on its long journey to us. The Planck satellite, WMAP more sensitive successor, was launched with the explicit goal of testing these anomalies with even greater precision. When its data was released, it largely confirmed the WMAP findings. The alignment was still there, slightly reduced in significance but stubbornly persistent. This made an instrumental error from a single mission far less likely, deepening the mystery rather than resolving it. If the alignment is real and cosmological in origin, the implications are staggering. It would suggest that either the cosmological principle is wrong and there is a preferred direction in the universe, or that the initial conditions of the universe were not random and Gaussian as inflation predicts. Some theorists have proposed truly mind-bending explanations. Perhaps our universe is not infinite and uniform, but has a non-trivial topology. It could be shaped like a donut or a pretzel, meaning if you traveled far enough in one direction, you would eventually return to your starting point. In such a finite universe, certain large-scale patterns could repeat and align. Even more radically, the alignment could be a bruise, a fossilized imprint from a collision with another universe in the multiverse before our own Big Bang, a pre-existing structure that set a preferred direction for our entire cosmic history. These are not ideas cosmologists entertain lightly. They are signs of how deeply puzzling this anomaly is, a crack in the otherwise smooth foundation of our understanding that suggests the universe might be keeping one last colossal secret about its true shape and origin. The axis of evil remains a quiet but persistent worry, a ghost in the machine of cosmology that reminds us that even our most cherished principles are ultimately hypotheses, waiting to be confirmed or overthrown by the next, deeper look into the cosmic dawn. Yet another paradox emerges not from what we see in the cosmos, but from the very nature of the most perfect voids within it, black holes. This puzzle strikes at the heart of physics itself, forcing a confrontation between our two most powerful and yet fundamentally incompatible theories, Einstein's general relativity and quantum mechanics. It's a problem so profound that it consumed the great Stephen Hawking for much of his career and remains one of the most active battlegrounds in theoretical physics today. This is the black hole information paradox, and it asks a deceptively simple question. When something falls into a black hole, is all information about it lost forever? To understand why this is such a catastrophic problem, we first need to understand a sacred rule of the quantum world, the principle of unitarity. In the quantum realm, information is never truly destroyed. It might be scrambled, transformed, or incredibly difficult to recover, but it is never erased from the universe. Think of it like burning a book. The ashes and smoke seem like a chaotic mess, but in principle, if you could collect every single atom and trace its path with perfect precision, you could reconstruct the original book. All the information is still there, just in a different form. Quantum mechanics insists the universe operates this way. The past always determines the future in a predictable, mathematical way. This reversibility is the bedrock of quantum theory. Now enter the black hole. According to Einstein's general relativity, a black hole is defined only by its mass, electric charge, and spin. This is the famous no-hair theorem. If you were to throw a grand piano, a computer, or a million-volume library into a black hole, the black hole would not gain piano-ness, computer-ness, or library-ness. It would simply get a tiny bit more massive and maybe change its spin a little. To an outside observer, every distinct object becomes identical once it crosses the event horizon. The unique information that described those objects appears to be completely obliterated, violating the core tenet of quantum mechanics. The paradox was sharpened to a fine point by Stephen Hawking's own revolutionary discovery. In 1974, Hawking made the stunning calculation that black holes are not completely black. Due to weird quantum effects happening just outside the event horizon, they slowly evaporate, emitting a faint glow of particles now known as Hawking radiation. This was a monumental achievement, weaving quantum mechanics into the study of gravity, but it created an even bigger problem. Hawking calculated that this radiation is purely thermal, it's random heat noise like the glow from a warm stove. It contains no information whatsoever about what fell into the black hole. As the black hole radiates, it loses mass and eventually evaporates completely. The terrifying conclusion Hawking initially reached was that all the information about everything that ever fell in is irrevocably lost, vanishing with the black hole's final pop. This would mean the universe is fundamentally unpredictable and quantum mechanics is wrong. Hawking famously bet fellow physicist Kip Thorne that information was indeed destroyed, a bet he would later recant. The potential resolution to this nightmare scenario is as bizarre as the paradox itself, and it comes from a concept called the holographic principle. This idea suggests that all the information describing a three-dimensional volume of space like the interior of a black hole might actually be encoded on its two-dimensional boundary, the event horizon. Imagine watching a thrilling, complex 3D movie, but the entire film is actually stored on the flat 2D surface of the DVD. The holographic principle posits that reality might work the same way. For a black hole, this would mean the information about the piano, the computer, and the library isn't lost inside the singularity. It is imprinted in a massively scrambled and complex way on the surface of the event horizon. As the black hole emits Hawking radiation, this radiation would actually interact with and carry away little bits of this encoded information, slowly and faithfully decoding the cosmic DVD over the immense timescale of the black hole's evaporation. Information is preserved and quantum mechanics is saved, but this elegant idea immediately spawned a new and terrifying puzzle, the firewall paradox. If information is slowly leaking out of the black hole via Hawking radiation, then by the time the black hole is halfway through its life, the radiation leaving now must be quantum mechanically entangled with the radiation that left earlier to preserve the information. But wait, that late-time radiation must also be entangled with the particles that fell into the black hole long ago, still hovering just inside the event horizon. In quantum mechanics, a principle called monogamy of entanglement forbids a particle from being fully entangled with two different systems at the same time. This creates an unbearable tension. To preserve the information for the outside universe, the outgoing radiation must be entangled with the early radiation. But for an astronaut falling in, the vacuum at the event horizon should be smooth and empty, meaning the outgoing radiation must be entangled with its infalling partner just inside the horizon. It can't be both. The proposed violent solution is that the event horizon is not a smooth place at all, but a searing wall of high-energy particles, a firewall, that would instantly incinerate any astronaut falling in. This would mean the event horizon is a physical boundary, not just a point of no return, radically altering our picture of black holes. The latest chapters in this story are being written with the tools of string theory, particularly through the study of what are called fuzzballs. This proposal does away with the idea of a point-like singularity and an empty event horizon entirely. Instead, string theory suggests that a black hole is a giant, tangled ball of strings, a fuzzball whose surface extends right to where the event horizon was thought to be. There is no vacuum inside, no singularity, and no sharp horizon. The entire interior of the black hole is a dense ball of stringy matter, and the information of what fell in is stored throughout this entire fuzzy structure. Hawking radiation then emanates from the surface of this fuzzball, naturally carrying away information without the need for a catastrophic firewall, resolving the paradox by reimagining the black hole's very structure from the ground up. The black hole information paradox is more than an academic debate. It is a crucial stress test for any theory that seeks to unify gravity and quantum mechanics. The eventual solution, whether it be holography, fuzzballs, or something beyond our current imagination, will not just tell us about black holes, but will fundamentally rewrite our understanding of the nature of reality, information, and space-time itself. From the holographic edges of black holes to the gravitational boundaries of our own solar system, we find yet another puzzle that defies easy explanation, a cliffhanger at the very frontier of our planetary neighborhood. Far beyond the orbit of Neptune, in the cold, dark realm of the outer solar system, lies a vast reservoir of icy remnants left over from the dawn of planet formation. This is the Kuiper Belt, a distant cousin to the asteroid belt but far larger and more massive, home to dwarf planets like Pluto, Haumea, and Makemake. For years, astronomers have been meticulously mapping this region, expecting to find a smoothly declining population of objects as they probe further from the Sun. Instead, they've run into a wall. At approximately 50 astronomical units from the Sun, that's 50 times the Earth-Sun distance, the number of Kuiper Belt objects, or KBO, doesn't just gradually thin out, it plummets. This sudden and dramatic drop-off is known as the Kuiper Belt Cliff, and its existence challenges our most fundamental models of how the solar system formed and what might lie beyond. The most straightforward explanation, of course, is that we're simply seeing the actual edge of the solar system's primordial building grounds. Perhaps the protoplanetary disk of gas and dust that swirled around our infant sun simply ended at this point, either because material was too sparse to coalesce further out or because some external force, like a passing star in the sun's birth cluster, stripped away the outer material. This would mean the cliff is a real physical boundary, a fossilized edge preserving the original size of the solar system's construction zone. The problem with this tidy answer is that it conflicts with other evidence. We have discovered a handful of extremely distant objects like the dwarf planet Sedna, whose bizarre, elongated orbits take them hundreds of O from the Sun before swinging back in. These objects couldn't have formed where their orbits currently are. The protoplanetary disk would have been far too thin. They must have formed closer in and been scattered outward by gravitational interactions. If that scattering process happened, logic dictates it should have filled the region just beyond 50 O with a significant population of similar objects. The fact that we see a cliff instead of a smooth distribution suggests something else is at work, actively clearing out that space. This is where the theories get far more exciting. The leading hypothesis is that the Kuiper Belt Cliff is not a natural edge but a carved one, sculpted by the gravitational influence of an as yet undiscovered planet. This is the same line of reasoning that led to the prediction of Planet 9, a hypothetical world with a mass several times that of Earth orbiting hundreds of O from the Sun. The gravitational pull of such a massive object could act as a shepherd, dynamically ejecting KBOs from the region just beyond 50 O, or pushing them into orbits that are too inclined or eccentric for our current surveys to easily detect. It would create a sharp edge to the main population, much like the gravitational shepherds among Saturn's rings create gaps and sharp edges in the ring structure. The cliff in this scenario is not a void but a signature, a gravitational fingerprint pointing toward a hidden architect of the outer solar system. However, before we get too carried away with visions of a new ninth planet, we must seriously consider a far more mundane possibility: that the Kuiper Cliff is an illusion, a product of our own observational limitations. Surveying the outer solar system is phenomenally difficult. These objects are incredibly faint, move very slowly against the background stars, and can only be seen when they are near their closest approach to the Sun in their long elliptical orbits. Our telescopes have primarily conducted surveys along the ecliptic, the flat plane in which most planets orbit. If a significant population of objects beyond 50 O have orbits that are highly tilted relative to this plane, our searches could have easily missed them, creating the false impression of a cliff when one doesn't truly exist. It's like searching for ships on the ocean by only looking directly along the horizon. You'd miss all the vessels sailing in the waters to the north and south. New, wider field surveys are just beginning to explore these off-plane regions, and their findings will be crucial in determining if the cliff is real or a selection effect. The resolution to this mystery lies in the delicate interplay between deeper observation and more sophisticated modeling. Next-generation telescopes like the Vera C. Rubin Observatory, currently under construction in Chile, promised to revolutionize this field. With its enormous mirror and massive digital camera, it will repeatedly scan the entire available sky, capable of detecting fainter and more distant objects than ever before. It should settle the debate once and for all, either revealing the hidden population of high-inclination objects that explain the cliff or confirming its stark reality. If the cliff is confirmed, the case for a perturbing planet, be it Planet 9 or something else, becomes immensely stronger. The Kuiper Belt Cliff is more than just a curiosity. It is a boundary line in a cosmic detective story. Whether it marks the limit of the sun's ancient nursery, the grazing edge of a hidden giant's influence, or simply the current limit of our own vision, its ultimate explanation will force us to redraw the map of our solar system and redefine our understanding of its tumultuous early history. From the distant, dark edges of our own solar system, we now journey inward to a world of stunning beauty and equally stunning peculiarity, to a storm of such geometric perfection it seems almost artificial. While Jupiter boasts its famous Great Red Spot, a colossal anticyclone that has raged for centuries, Saturn offers a meteorological marvel that is, in many ways, even more bizarre. At its north pole, shrouded in shadow for years at a time, rages a hurricane wider than the entire Earth, but it is not the storm's size that defies belief, it is its shape. For over 4 decades since the Voyager probes first glimpsed it, this vast maelstrom has been locked into a near-perfect, stable, 6-sided hexagon. This is not a feature painted on a celestial billiard ball. It is a towering jet stream of screaming winds, a 6-sided wall of cloud tracing a path around the pole with an almost mathematical precision that nature simply isn't supposed to produce on such a grand scale. The sheer scale of this structure is difficult to comprehend. Each side of the hexagon is longer than the diameter of our planet. The winds that form its boundaries whip around at speeds exceeding 200 miles per hour, channeled into this bizarre polygonal path rather than the more typical oval or circular patterns we see in other planetary storms. Perhaps the most baffling aspect is its incredible longevity. First observed by Voyager in the early 1980s, it was still there, unwavering, when the Cassini spacecraft arrived over 25 years later. It has persisted through decades of Saturn's long seasonal cycles, a permanent feature etched onto the planet's face. This endurance is the true heart of the mystery. Most atmospheric phenomena, even the largest, are transient. Clouds form and dissipate, storms merge and break apart. The Saturn hexagon, however, is a permanent tattoo, a deeply rooted feature of the gas giant's atmospheric engine that has outlasted every human effort to study it. So how does a fluid atmosphere, governed by the chaotic laws of turbulence, spontaneously organize itself into a geometric shape and then hold that form for generations? The search for answers has led physicists not only to supercomputer models but also back to the laboratory bench. Researchers have found they can create startlingly similar shapes right here on Earth using a very simple setup, a circular tank of fluid placed on a rotating table. As the table spins, representing the rotation of the planet, the fluid in the center moves faster than the fluid at the edges, creating a shear gradient. When this rotating fluid is stirred or subjected to a current, something remarkable happens. Under the right conditions, the flow doesn't break into a series of messy eddies. Instead, it self-organizes into stable polygons, triangles, squares, and yes, hexagons. The number of sides depends on the differential in rotation speeds, with a hexagon appearing at a specific critical threshold. This suggests the hexagon is a type of standing wave, a stable pattern that emerges from the complex interplay between the deep-rooted rotation of Saturn itself and the faster-moving jet streams in its upper atmosphere. It is a natural, if rare, outcome of fluid dynamics on a rotating sphere. The Cassini spacecraft, which spent over 13 years orbiting Saturn, gave us an unprecedented view of this phenomenon, revealing that the hexagon is not a flat, two-dimensional feature but a towering structure that extends deep into the atmosphere, likely hundreds of kilometers down. More fascinating still were the observations of how this colossal shape changed with Saturn's seasons. For years, the North Pole was plunged into the darkness of its long winter, with the hexagon hidden from view. But as the season turned toward spring and sunlight finally reached the polar region, Cassini's infrared and visible light cameras watched the hexagon seemingly come to life. The once dark interior of the shape began to glow with a hazy, blue tint as sunlight catalyzed the formation of high-altitude photochemical smog. Meanwhile, the central hurricane at the pole, with its own distinct eye, became visible. The changing sunlight revealed the hexagon not as a static painting, but as a dynamic, layered atmospheric factory, with different processes occurring at different altitudes, all contained within its immovable geometric walls. This leads to a final, compelling question. If this is a natural phenomenon of rotating fluids, why don't we see similar features on other gas giants? Jupiter, Uranus, and Neptune all rotate rapidly and have turbulent atmospheres with powerful jet streams. Yet no persistent polygonal shapes have been observed at their poles. The answer may lie in the unique character of Saturn's atmosphere. Compared to Jupiter, Saturn's weather layer is much deeper and may have less internal friction or a different thermal structure, allowing a standing wave like the hexagon to form and stabilize without being disrupted by deeper chaos. Alternatively, the specific latitudinal profile of Saturn's winds, the precise speed and shear of its jets, might hit that sweet spot for hexagonal formation that the other giants simply do not. It's possible that similar features did exist on other planets but were transient, failing to lock in for the geological timescales that Saturn has enjoyed. The Saturn hexagon stands as a breathtaking example of how the fundamental laws of physics can conspire to create something that looks utterly unnatural. It is a cosmic coincidence of rotation, wind shear, and atmospheric depth, a pattern written in the clouds that continues to challenge our understanding of fluid dynamics on a planetary scale. Yet while Saturn's hexagon presents a puzzle of beautiful, persistent structure, our next mystery takes us to a world defined by its desolation, a barren, rust-colored landscape that may be hiding a secret with profound implications. The discovery of methane gas on Mars is a scientific cliffhanger that has been unfolding for decades, a tantalizing whiff of something that, on Earth, is overwhelmingly produced by living organisms. This isn't just about finding a simple gas. It's about chasing a ghost, a signal that appears and vanishes with a maddening inconsistency that has left researchers grappling with two equally revolutionary possibilities. Is it the signature of hidden, subterranean life, or the product of exotic geology that we barely understand? The story begins not with a bold announcement, but with a series of tentative, contested detections. Early observations from Earth-based telescopes and the European Space Agency's Mars Express orbiter in the early 2000s reported faint, elusive plumes of methane in the Martian atmosphere. The scientific community met these claims with healthy skepticism. Mars has a thin atmosphere that is constantly bombarded by ultraviolet radiation from the sun, a process that creates highly reactive chemicals that should destroy methane molecules within a few hundred years. For methane to be present at all, it must be actively and recently replenished by some ongoing source. This made every detection explosive because it implied something on Mars was producing methane now. The quest for answers found its most powerful detective in NASA Curiosity rover. Since landing in Gale Crater in 2012, its sample analysis at Mars Instrument Suite, a sophisticated portable chemistry lab, has been sniffing the thin Martian air. Its data has transformed the mystery from a question of if to a question of how and why. Curiosity has confirmed the presence of methane, but not as a constant background gas. Instead, it detects it in unpredictable, sudden spikes. Levels will jump from a background of less than 1 part per billion to 10 parts per billion over the course of a few Martian days, only to disappear just as quickly. Even more intriguingly, the rover has revealed a clear seasonal pattern in the background level of the gas, with concentrations peaking during the Martian summer and dropping in the winter. This cyclical behavior points to a complex process of release and destruction, a hidden methane cycle operating just beneath our feet. So what is creating this gas? The debate hinges on two very different pathways. The biological explanation is the most thrilling. On Earth, the vast majority of atmospheric methane is produced by methanogens, ancient microbes that metabolize hydrogen and carbon dioxide and exhale methane as a waste product. Could similar primitive microbial life exist deep underground on Mars, protected from surface radiation, living in water-filled pores within rocks and producing these intermittent belches of gas that curiosity detects? The idea is not as far-fetched as it seems. Such ecosystems thrive deep underground on Earth without any need for sunlight. The seasonal variation could then be explained by changes in surface pressure or temperature that affect how the gas diffuses upward from its subsurface source. The alternative and currently preferred explanation lies in the field of geology, specifically a process called serpentinization. This is a chemical reaction between water, carbon dioxide, and the mineral olivine, which is common in volcanic rock. When these ingredients are present under the right conditions of temperature and pressure, they can react to form serpentine minerals and, as a byproduct, methane. This process requires no biology whatsoever. It is simple abiotic chemistry. Mars has plenty of water ice and the right kinds of rock, making serpentinization a perfectly plausible candidate. The seasonal spikes could be caused by small amounts of subsurface brine melting in the summer heat and percolating down through cracks to reach these reactive minerals, triggering a burst of gas production. The plot thickens considerably when we bring another robotic scientist into the story, the Trace Gas Orbiter. This advanced European-Russian satellite arrived at Mars in 2016 with a specific primary goal: to map Martian atmospheric gases with incredibly high sensitivity and to finally solve the methane mystery from orbit. To the immense frustration of scientists everywhere, its initial years of data turned up nothing. It detected no methane whatsoever, not even the faint background levels Curiosity was measuring from the surface. This stark contradiction is not a case of one instrument being wrong. It's a clue that the mystery is even more complex than we imagined. One compelling resolution to this contradiction involves timing and destruction. The orbiter's measurements are taken during the Martian day, while Curiosity's ground-level measurements often catch spikes at night. It's possible that the methane releases are so localized and brief that they are quickly diluted and destroyed by the time the sun rises and the orbiter passes overhead. The intense ultraviolet radiation at the surface could be breaking the methane down within hours, creating a thin, ephemeral haze that only a lander sitting right in the midst of it could catch. Alternatively, the gas could be absorbed by the salty regolith on the surface during the day and then released at night, creating a layer of gas just above the ground that an orbiter high above would never see. This ongoing detective story, with its conflicting evidence and vanishing clues, is a perfect example of the scientific process at its most challenging and exciting. It has forced us to develop better instruments, to question our assumptions, and to consider the unique and weird environmental conditions of another world. The implications of either answer are staggering. If the source is geological, it reveals a Mars that is far more chemically active and hydrated than we ever believed, with ongoing water-rock interactions that could potentially provide energy and resources for future human exploration. But if the source is biological, it would mean that life is not a singular miracle confined to our world, but a cosmic phenomenon that can arise independently on neighboring planets. It would fundamentally change our understanding of our place in the universe. The Martian methane is a whisper, a faint signature in the wind that we are straining to hear. Each new detection and non-detection adds another piece to a puzzle that is reshaping our understanding of the red planet, reminding us that the greatest discoveries are often not shouted but breathed. For decades, the cornerstone of modern cosmology has been the undeniable presence of dark matter. We've seen its gravitational hand shaping the rotation of galaxies, bending the light from distant objects, and forming the vast cosmic web upon which visible matter is merely draped. Its existence is woven into the very fabric of our understanding of the universe. So, imagine the profound confusion when astronomers stumbled upon a galaxy that appeared to be naked. A galaxy utterly devoid of this invisible, defining substance. This isn't a small puzzle. It's a direct challenge to the rules we thought governed how every galaxy is built. The story begins with a peculiar, diffuse galaxy known as NGC 1052 DF2, or DF2 for short, discovered by the Dragonfly Telephoto Array, a telescope specifically designed to find extremely faint objects. DF2 looked like a ghostly smudge of light. When Pieter van Dokkum of Yale University and his team turned the powerful Keck Observatory toward it to measure the motions of its star clusters, they expected to see the telltale signs of dark matter's pull. The method is standard. By measuring how fast these clusters orbit the galaxy's center, you can calculate the total mass pulling them inward. The faster they move, the more mass, both visible and dark, must be present to hold them in place. To their astonishment, the star clusters in DF2 were moving at a leisurely, sedate pace. The calculated mass needed to account for this slow motion was almost exactly equal to the mass of all the visible stars they could see. There was simply no room left for dark matter. The result was so shocking that the team spent a year testing and retesting their data, searching for any possible error. They even went on to find a second such galaxy, DF4, which displayed the same bizarre characteristic. It seemed they had found a class of celestial objects that defied the most fundamental model of galaxy formation. The immediate reaction from the scientific community was understandably intense skepticism. The primary counter-argument was a simple one: perhaps the distance to these galaxies was wrong. The entire calculation hinges on knowing exactly how far away the galaxy is. Get the distance wrong, and all your velocity and mass calculations are thrown off. If DF2 were much closer to us than initially believed, then its stars would be intrinsically dimmer, meaning there's less visible mass than we think. This would force us to invoke the presence of dark matter to explain the observed star motions, making it a normal galaxy after all. This debate over distance measurements raged for some time, with different teams using different methods arriving at conflicting results. However, more recent and precise observations, including those from the Hubble Space Telescope, have largely confirmed the original distance estimates, strengthening the case that these galaxies are indeed anomalous. If we accept that these dark matter-deficient galaxies are real, the next question is the most thrilling. How could such a thing even form? Our standard model of cosmology, known as the lambda cold dark matter model, posits that galaxies are born within immense halos of dark matter. The gravity of these halos draws in ordinary gas, which then cools and condenses to form stars. The dark matter is the foundation. The visible galaxy is just the glittering decoration on top. A galaxy without dark matter turns this entire process upside down. One compelling theory involves a violent galactic encounter. Perhaps a small galaxy was born normally with its own dark matter halo, and then had an extremely close encounter with a much larger galaxy. The gravitational tides from the larger neighbor could have violently stripped away both the dark matter and the faint outer stars of the smaller galaxy, leaving behind only the dense, bright core, which then drifted away to become the oddball we see today. In this scenario, DF2 and its kin aren't primordial freaks. They are the survivors of a cosmic hit and run, their dark matter stolen from them in a gravitational mugging. Another fascinating possibility is that these galaxies formed in a completely different way from a mechanism known as a tidal dwarf. When two large galaxies collide, the tidal forces can pull streams of gas and stars out from their main bodies. This ejected material, now devoid of the dark matter from the original halos, can sometimes collapse under its own gravity to form a new, small galaxy. These second-generation objects would be made purely from the polluted baryonic matter of their parents, naturally explaining their lack of dark matter. Finding such a galaxy would be like finding a child that genetically inherited nothing from its grandparents, only the blended traits of its parents. The existence of these galaxies, if confirmed, actually provides a surprising and robust piece of evidence for the existence of dark matter itself. Think about it. If the phenomena we attribute to dark matter were actually caused by a modification to the laws of gravity, such as the proposed theory of modified Newtonian dynamics or MUND, then every galaxy should obey these new rules. There should be no outliers. The fact that the vast majority of galaxies behave as if they are filled with dark matter, while a small handful like DF2 behave as if they are not, is a huge problem for MUND. A modified gravity theory would predict a smooth, universal behavior. The existence of galaxies that perfectly follow the old Newtonian rules of gravity without any need for modification suggests that dark matter is indeed a thing, a substance that can be present or absent, and not just a rewrite of the physics textbooks. In a strange way, the galaxies without dark matter might be the strongest proof that dark matter is real for everyone else. This discovery forces us to confront the beautiful complexity of the universe. It tells us that while our models are powerful, they are not perfect, and nature always has a few surprises waiting in the wings. The hunt is now on to find more of these paradoxical galaxies and to study them in exquisite detail. Each one is a natural laboratory, a unique test case that allows us to study the behavior of visible matter all on its own, free from the overwhelming gravitational influence of the dark variety. They are the exceptions that prove the rule, the outliers that, by their very strangeness, help us better define the normal. In the end, the galaxy without dark matter doesn't break cosmology. It challenges us to refine it, to understand the myriad ways in which the cosmic dance between light and shadow can play out across the vast expanses of space and time. Yet this seemingly straightforward prediction runs into a glaring, persistent problem when we look out at the actual universe. According to the models, the protons and neutrons fused in that first cosmic furnace should have left behind a specific, measurable abundance of these light elements. For hydrogen and helium, the predictions are spectacularly accurate. When astronomers measure the primordial helium in clouds of ancient gas or in the oldest stars, the numbers line up almost perfectly with what Big Bang nucleosynthesis calculated. This incredible success gave scientists immense confidence in the entire Big Bang model. But for lithium, the story is completely different. The observed amount of lithium-7 in the oldest stars in our galaxy, stars that formed from nearly pristine material early in the universe's history, is only about 1/3 of what the theories predict. It's as if the universe followed the recipe perfectly for hydrogen and helium, but somehow lost over half the lithium along the way. This isn't a small rounding error. It's a factor of 3 discrepancy that has stubbornly resisted explanation for decades, becoming a classic unsolved problem in cosmology known as the cosmic lithium problem. To appreciate the depth of this mystery, we need to understand how we know what the primordial lithium abundance even is. We can't go back in time to measure it directly, so astronomers act as cosmic detectives, searching for the most ancient crime scenes, stars that have been preserved since nearly the dawn of the galaxy. The best laboratories for this are metal-poor population 2 stars, and particularly a rare subclass known as ultra-metal-poor stars. The term metal here is astronomers speak for any element heavier than helium. A star with very low metallicity formed from gas that had been minimally polluted by previous generations of stars. It is a nearly pristine sample of the early universe's composition. By pointing powerful spectroscopes at these ancient suns, scientists can analyze the specific wavelengths of light they absorb, which reveals their chemical makeup. The amount of lithium they contain is, in theory, the amount that was present when they formed, and across the board, in star after ancient star, the measured lithium abundance is consistently and bafflingly low. This leaves us with a compelling puzzle. Where did all the lithium go, or was it never made in the predicted amounts to begin with? The search for an answer has branched into two distinct avenues of investigation. The first avenue explores the possibility that the lithium was indeed created as predicted, but was then destroyed sometime after the Big Bang before we could get a clean measurement of it. The prime suspects in this scenario are the stars themselves. As lithium is a fragile element, it can be easily destroyed in the hot interiors of stars. If the surfaces of these ancient stars were somehow mixed with their hotter inner layers over their multi-billion-year lifetimes, the lithium could have been burned away. Some theories propose that certain types of pre-main sequence stars or exotic physics like atomic diffusion could have gradually transported surface lithium down into the furnace below, effectively erasing the original signature. However, this stellar destruction theory has its own problems. The oldest stars we observe show a remarkably consistent lithium abundance, the so-called Spite Plateau, named after the astronomers who first identified it. If stellar processes were efficiently destroying lithium, we would expect to see a much wider spread in the measurements, dependent on each star's individual mass, age, and rotational history. The tightness of the plateau suggests we are seeing the original, unaltered value, making the case for post-Big Bang destruction more difficult to prove. The second and more radical avenue questions the initial nuclear cooking process itself. Perhaps our understanding of the physics in the universe's first few minutes is incomplete. The predictions of Big Bang nucleosynthesis rely on a precise knowledge of nuclear reaction rates and the conditions of the early universe. Could an unknown particle have been present that altered these reactions? One tantalizing proposal involves the potential decay of exotic, massive particles that may have existed in the early cosmos. For instance, certain supersymmetric particles like the neutralino could have decayed and released electromagnetic energy, effectively changing the ratio of protons to neutrons and lowering the final yield of lithium-7. Another possibility is that our measurements of key nuclear cross-sections, the probabilities that certain fusion reactions will occur, are slightly off. The specific reaction chain that creates lithium-7 is delicate, and a small error in our laboratory measurements of these nuclear rates could propagate through the entire model, leading to a significantly different prediction. Researchers are constantly refining these experiments to see if they can close the gap. The lithium problem forces us to confront the limits of our knowledge in a truly fundamental way. It pits the incredible success of the overall Big Bang model against a specific, nagging inconsistency that refuses to vanish. Resolving it could require a subtle tweak to our nuclear physics textbooks, or it could be the first tiny crack leading to a monumental discovery in particle cosmology, a hint of new physics operating at energy scales we can never hope to achieve in a terrestrial collider. It serves as a powerful reminder that even our most successful scientific theories are not closed books, but living frameworks, constantly tested and refined by the unforgiving light of data from the farthest reaches of space and time. Each ancient star with its faint lithium line is a messenger from the dawn of everything, carrying a code we have not yet fully broken. After confronting the paradox of galaxies seemingly devoid of dark matter, we now turn our attention to an entire class of cosmic phantoms that challenge our very definition of what a galaxy can be. These are the ultra-diffuse galaxies, or UDG, and they are among the most enigmatic inhabitants of the universe. Imagine a galaxy the size of our own Milky Way, a sprawling disk spanning 100,000 light-years. Now, imagine that instead of containing hundreds of billions of brilliant stars, it holds only 1% of that number, a mere few billion stars spread so thinly across that vast volume that the entire structure becomes almost transparent, a wispy ghost of a galaxy against the blackness of space. These are not failed galaxies, they are galaxies that chose a path of extreme minimalism, and their existence forces us to ask how such fragile structures can possibly survive in the violent cosmic environment. The story of their discovery is a tale of technological perseverance. For decades, these faint ghosts were literally invisible to our telescopes. Their surface brightness is so incredibly low that they blurred into the background glow of the night sky itself. It wasn't until the advent of supremely sensitive instruments, like the Dragonfly telephoto array, which uses clusters of off-the-shelf camera lenses specifically designed to suppress scattered light, that these ethereal objects began to emerge from the darkness. Dragonfly's surveys of the Coma cluster, a dense gathering of thousands of galaxies, revealed a startling population of these UDGs, hovering like vast, faint smudges between their brighter, denser cousins. Their discovery was a revolution in census-taking, revealing a population of galaxies we never knew was there, hidden in plain sight. The immediate and pressing question is one of structural integrity. How does a galaxy with so few stars, and therefore so little gravitational pull from its visible matter, hold itself together? According to all our models, the gravitational tides within a massive cluster like Coma are unimaginably powerful. A normal galaxy with so little stellar mass should have been ripped apart eons ago, its stars scattered into the intracluster void. The fact that these UDGs not only exist but are quite common within clusters suggests they must be held together by something else, something invisible providing the necessary gravitational glue. For many of these galaxies, the answer seems to be an overwhelming amount of dark matter. Observations of their rotation and the motions of their star clusters indicate that some UDGs are among the most dark matter-dominated objects in the universe. They are essentially massive, invisible halos of dark matter that, for reasons we don't understand, manage to attract only a tiny sprinkling of stars. They are all shadow and almost no substance cosmic stealth fighters built from material we cannot see. But just as we begin to accept this neat explanation, the plot twists spectacularly. Recall the mysterious galaxies like DF2 and DF4 that we discussed earlier, which appear to have no dark matter at all. It turns out that many of these oddballs are also ultra-diffuse galaxies. They have the same large size and pitifully few stars, but their internal dynamics reveal a terrifying void where dark matter should be. This presents us with a schism, a deep and puzzling dichotomy within the same class of object. We have two types of UDGs, one type that is drowning in dark matter, and another type that is almost completely empty of it. This duality is a nightmare for theorists, as it suggests that the path to forming such a diffuse structure is not one, but at least two completely different roads. So how do we get these two opposite extremes? For the dark matter-rich UDGs, the leading theory is that they are failed galaxies. They may have formed within perfectly normal, massive dark matter halos early in the universe. But perhaps they resided in a particularly barren region of the cosmic web where there was very little gas to be drawn in to form stars. Or, if they live in a cluster, the dense intergalactic environment may have stripped away their gas reservoirs early in their lives, starving them of the fuel needed to build a large stellar population. What remains is a massive dark matter halo that never got to dress itself in bright lights. The dark matter-poor UDGs, on the other hand, require a far more dramatic origin story. One compelling idea is that they are tidal dwarfs. When two large galaxies have a violent gravitational dance, they can rip huge streams of gas and stars out of each other. This ejected material, which originally came from the star-rich disks of the parent galaxies, is naturally devoid of dark matter. If this tidal debris collapses under its own gravity, it can form a new, entirely distinct galaxy, a second-generation object built purely from the recycled stuff of its parents. These galaxies would be born large and diffuse and made only of baryonic matter, perfectly matching the bizarre profile of a dark matter-free UDG. The existence of these ghostly galaxies in both their forms is more than just a curiosity. It is a powerful stress test for our entire understanding of galaxy formation. The dark matter-rich variety tells us that the process of star formation is inefficient and can be stifled by environment, leaving behind the raw gravitational scaffolding of dark matter for us to study. The dark matter-poor variety tells us that galaxies can be born from the debris of cosmic collisions, and that not everything in the universe needs a dark matter anchor to exist. Together, they paint a picture of a far more diverse and complex cosmic ecosystem than we ever imagined, a universe capable of building the same faint, sprawling structure through two utterly different and opposing means. They are the gentle giants of the cosmos, whispering two different secrets about the hidden forces that shape our universe. Yet another crack in the seemingly smooth edifice of our cosmological model has been widening into a potentially paradigm-shattering chasm, one that pits the ancient universe against the modern one in a battle of measurements. This is the Hubble tension, and it is not merely a statistical fluke. It is a stubborn, growing discrepancy in one of the most fundamental numbers in all of cosmology, the Hubble constant, which defines the current rate of the universe's expansion. For over a decade, as our tools for measuring this rate have become exquisitely precise, a worrying split has emerged. Two completely independent, gold-standard methods for measuring how fast the cosmos is growing are now returning answers that disagree with a confidence level exceeding 5 sigma, meaning there is less than a 1 in a million chance that this is a random error. It's as if two of the world's most accurate clocks, built on different principles, began ticking at undeniably different speeds, forcing us to question whether we understand the mechanisms of time itself. The first method looks back to the very beginning, using the cosmic microwave background as its Rosetta Stone. The Planck satellite, which mapped the CMB with phenomenal detail, allows scientists to calculate the Hubble constant by working within the standard lambda-cold dark matter model of the universe. They take the precise measurements of the fluctuations in the ancient light and run the cosmic movie forward, factoring in the known effects of dark matter and dark energy. This model-dependent approach gives them a predicted expansion rate for the universe today of about 67.4 kilometers per second per megaparsec. This means that for every megaparsec of distance, a mind-boggling 3.26 million light-years, a galaxy is moving away from us at 67.4 kilometers per second faster. The second method builds a distance ladder to measure the expansion rate directly in our local, modern universe. This is a painstaking, multi-rung process that starts with measuring the distances to nearby Cepheid variable stars. Stars whose pulsation periods are directly tied to their intrinsic brightness. By knowing how bright they truly are and comparing it to how dim they appear from Earth, astronomers can calculate a precise distance. These Cepheids are then used to calibrate the next rung on the ladder, often type 1, a supernova, which are even brighter and can be seen in galaxies much farther away. The most recent results from this ladder, most notably from the SH0ES collaboration led by Adam Rees, have consistently found a higher value, around 73 kilometers per second per megaparsec. The difference of about 5.5 kilometers per second might seem small, but in the world of precision cosmology, it is a monumental gulf that refuses to close. This discrepancy has launched a massive scientific effort to find a systematic error, an unaccounted-for flaw in one of the measurement techniques. Perhaps our understanding of Cepheid variables is incomplete. Maybe there is unknown dust dimming the supernova in a way we haven't corrected for, or perhaps the supernova themselves are not perfectly standard candles. Teams have invented entirely new methods to cross-check the results, using the subtle geometry of light echoes from red giant stars or the gravitational lensing of distant quasars. Astonishingly, these independent techniques are beginning to cluster around the higher local value, deepening the tension rather than resolving it. It is becoming increasingly difficult to blame this on a simple measurement error. The evidence is pointing toward a far more exciting possibility, that this is not a mistake but a discovery. The Hubble tension may be the first observable sign that our standard model of cosmology, for all its success, is incomplete. If new physics is indeed required, theorists have begun exploring breathtaking possibilities that would rewrite our understanding of the cosmos. One compelling idea involves a late-time interaction or evolution of dark energy. What if dark energy is not a constant cosmological force, but a dynamic field that has grown stronger over time? This increased push would have accelerated the expansion more recently than the standard model accounts for, explaining why our local measurements show a faster rate than what is predicted from the early universe's initial conditions. Another proposal involves early dark energy, a transient form of energy that may have existed for a brief period shortly after the Big Bang, altering the sound horizon of the primordial universe, a fundamental ruler used in the CMB calculations, and thus throwing off the Planck prediction. Other ideas venture into the realm of particle physics, suggesting that dark radiation, perhaps from unknown, lightweight particles like sterile neutrinos, could have influenced the early universe's expansion history, creating a subtle mismatch that only manifests now as this tension. The implications of solving this puzzle are profound. Confirming the Hubble tension as real new physics would be one of the most significant discoveries in cosmology since the detection of the universe's accelerating expansion. It would force a major revision of the lambda CDM model, potentially revealing a richer, more complex nature for dark energy, or exposing the existence of entirely new particles that shaped the cosmos in its first moments. It represents a thrilling moment in science where a persistent anomaly refuses to be ignored, pushing researchers to question their most fundamental assumptions and daring them to imagine a universe even stranger and more wonderful than we currently believe. The Hubble tension is more than a numbers game. It is a potential window into the next great revolution in our understanding of everything. Now we turn our gaze from the deep cosmos back to our own solar system, to a mystery that begins not with what we see, but with what we can't: a ghost planet, a gravitational specter whose presence is inferred only by the bizarrely orchestrated dances of small, icy worlds billions of miles away. This is the hunt for Planet 9, a hypothetical giant whose discovery would be the most significant addition to our solar system since the finding of Neptune in 1846, and one that would force a complete rewrite of our solar system's history. The story doesn't start with a single anomalous object, but with a peculiar pattern emerging from the frigid darkness of the distant Kuiper belt. Astronomers tracking the orbits of the most far-flung objects, those with average distances from the Sun far beyond Neptune, began to notice something strange. Their orbits weren't just randomly oriented as one would expect from billions of years of gravitational jostling. Instead, the long axes of their highly elliptical paths appeared to be physically clustered together, all pointing in roughly the same general direction. Even more bizarrely, these orbits were all tilted in a similar way, leaning over at almost the same angle relative to the flat plane of the solar system. Statistically, the odds of this happening purely by chance are astronomically low, less than 0.0002%. It's as if you threw a handful of pencils onto a table and they all landed pointing northwest. This gravitational fingerprint strongly suggests that the orbits of these distant objects are being shepherded, their paths shaped and organized by the persistent, gentle tug of a massive, unseen object. The hypothetical planet needed to create this effect would be a true giant, a world with a mass estimated at 5 to 10 times that of Earth. This would place it somewhere between a super-Earth and a mini-Neptune, a class of planet common around other stars but thought to be absent from our own neighborhood. Its orbit would be immense, taking between 10,000 and 20,000 years to complete a single journey around the Sun, and highly elliptical, swinging from a perihelion of maybe 200 to 300 out to an aphelion of over 600 or even 1,200. From our perspective, it would move incredibly slowly against the backdrop of stars, a key reason it has eluded discovery for so long. Its gravitational influence would be felt not only in the clustered orbits, but also in creating a population of objects with orbits perpendicular to the solar system's plane, a prediction that has since been borne out with the discovery of several such objects, adding more weight to the hypothesis. This is not the first time such a method has been used to predict a planet. The discovery of Neptune itself was a triumph of mathematical prediction, where astronomers Urbain Le Verrier and John Couch Adams calculated its position based on anomalies in the orbit of Uranus. The search for Planet 9 is a modern, far more difficult version of that same celestial detective work. Today's hunt is a monumental effort, combing through petabytes of data from powerful wide-field survey telescopes like Pan-STARRS in Hawaii and the soon-to-be operational Vera C. Rubin Observatory in Chile. These instruments are systematically photographing the entire available night sky, night after night, looking for that one faint, slow-moving dot among millions of stars. It is a needle in a haystack search of epic proportions, but the potential reward, a new planet in our own solar system, is worth the immense effort, of course. Such a radical idea invites healthy skepticism and alternative explanations. Some astronomers propose that the observed clustering could be a result of observational bias, that we've only found a handful of these extreme objects, and our limited search patterns have simply missed others that would fill in the pattern and make it look random. Others have suggested that the collective gravity of many smaller, unseen objects in the outer Kuiper belt could, over vast timescales, create the same shepherding effect as one large planet. There's even a more exotic possibility that the gravitational culprit isn't a planet at all, but a primordial black hole, a leftover relic from the Big Bang with the mass of a planet but only the size of a grapefruit, whose gravitational pull would be identical. Yet the Planet 9 hypothesis remains the most compelling and testable explanation. If it is found, its implications would be staggering. A planet of that size and on such a distant orbit could not have formed where it is now. The protoplanetary disk around the infant sun would have been far too sparse. This means Planet 9 must have been born much closer in, alongside Jupiter and Saturn, and was then violently flung out into the distant hinterlands by a gravitational slingshot interaction with one of the gas giants in the solar system's chaotic youth. Its existence would be a frozen record of a dramatic, unstable chapter in our solar system's formation, a time of planetary pinball that we are only just beginning to appreciate. Finding Planet 9 would do more than just add a new world to our charts. It would reveal a violent, dynamic birth for our cosmic home that we never knew existed, a secret held in the silent, synchronized orbits of the solar system's farthest outposts. Moving from the grand, chaotic spirals of galaxies and the hypothetical pull of a distant planet, we now zoom in on a single, breathtaking celestial object that presents a mystery of stunning geometric perfection. In the constellation Monoceros, the Unicorn, lies one of the most peculiarly beautiful sights in the cosmos, the Red Rectangle Nebula. From its very discovery, this object has defied all expectations. Most planetary nebulae, the glowing, expanding shells of gas shed by dying stars, boast ethereal, irregular shapes, billowing spheres, intricate bipolar lobes, or chaotic, twisting patterns. The Red Rectangle, as its name bluntly states, is different. Through a telescope, it doesn't look like a cosmic cloud at all. It appears as a series of nested, sharp-cornered rungs on a ladder, forming a structure of such precise symmetry it seems almost engineered. This is not a place of soft edges and gentle glows. It is a cosmic cathedral built with a ruler and a compass, and its existence challenges our understanding of the final, dramatic acts of a star's life. At the heart of this geometric marvel lies not one but two stars locked in a tight gravitational embrace. This binary system, known as HD 44179, is the engine power the entire spectacle. The primary star is a post-AGB star, a sun-like star that has passed through the red giant phase and is now in its final death throes, shedding its outer layers into space. Its companion is a smaller main sequence star. It is the complex interaction between these two dancers that is believed to be the master architect of the nebula's bizarre form. As the dying primary star puffs out vast clouds of gas and dust in a spherical outflow, its companion star's gravity acts like a sculpting tool, funneling this material into two opposing cones or hourglass shapes. Our perspective from Earth looks directly down the barrel of this hourglass, causing the sharp, rung-like edges to appear as a rectangle. The rungs themselves are thought to be waves of density, like ripples in a pond, created by periodic eruptions from the central system or by the precise orbital mechanics of the binary pair, which has a period of about 10.3 months. But the mystery of the red rectangle isn't just its shape, it's also its profound and startling color. The deep crimson hue that gives the nebula its name is extraordinarily rare in the universe. This intense red emission doesn't come from the common nebulous glow of hydrogen gas, but from something far more exotic, a class of complex organic molecules known as polycyclic aromatic hydrocarbons, or PAH. These are not signs of life, but rather large carbon-based molecules made up of interconnected rings of carbon atoms, essentially soot-like compounds. The red rectangle is a factory for producing these molecules, and the harsh ultraviolet light from the hot central star causes them to fluoresce, emitting a characteristic red light. The presence of these PAHs in such abundance makes this nebula a crucial laboratory for astrochemistry, showing us how the complex molecular building blocks of life, the very carbon that makes up our bodies, can be forged and disseminated into the interstellar medium from the death of stars. The latest high-resolution observations from the Hubble Space Telescope have only deepened the intrigue, revealing that the nebula is not a static sculpture but a dynamic, evolving structure. The seemingly solid rungs are actually a series of concentric expanding shells, like the layers of a cosmic onion being shed over time. Furthermore, the base of the entire structure shows a distinct X shape, suggesting that the sculpting process is even more complex than a simple hourglass, possibly involving processing jets or a warping accretion disk around one of the stars. For astronomers, the red rectangle is a gift and a challenge. It represents a fleeting phase in stellar evolution, a moment frozen in time that might only last a few tens of thousands of years. By studying it, we gain invaluable insight into the shaping of bipolar nebulae, the processing of stardust into complex organics, and the profound influence of binary stars on the death of their companions. It stands as a majestic reminder that even in its final moments, a star can create something of breathtaking order and beauty, a geometric whisper against the chaotic backdrop of the cosmos. Yet as we ponder the possible origins of these unimaginable particles, we immediately run into a paradox so severe it bears the name of its discoverers, the Greisen-Zatsepin-Kuzmin, or GZK cutoff. This isn't just a mystery, it's a cosmic speed limit, a fundamental barrier imposed by the universe itself. The logic is devastatingly simple. An ultra-high-energy cosmic ray, say a single proton traveling at 99.9999999% of the speed of light, is not moving through empty space. It is barreling through a universe filled with the faint, cold afterglow of the Big Bang, the cosmic microwave background radiation. These CMB photons may be low energy, but from the perspective of a proton moving at near light speed, they are dramatically blue-shifted. To our ultra-relativistic proton, the placid CMB is transformed into a raging storm of high-energy gamma rays. When such a proton collides with one of these blue-shifted photons, the resulting interaction is powerful enough to produce new particles, specifically pions. This process saps the proton's energy, effectively putting a hard cap on how far it can travel before its energy drops below a certain threshold. The math is clear. A proton with an energy above about 8 times 10 to the 19th electron volts should be able to travel no more than 150 million light-years before the CMB acts as a kind of cosmic friction, bleeding away its incredible energy. This distance is a mere stone's throw in cosmological terms. This is where the paradox sharpens to a fine point. When we map the arrival directions of these ultra-high-energy cosmic rays, we do not find them coming from a neat, local bubble within 150 million light-years of Earth. Our galactic neighborhood is relatively sparse, lacking the extreme astrophysical engines like near-by-active galaxies or powerful quasars that could plausibly accelerate particles to such energies. Furthermore, the trajectories of these particles are notoriously difficult to trace. Cosmic rays are charged particles, so their paths are bent and scrambled by the magnetic fields that permeate intergalactic space, making it nearly impossible to pinpoint their exact source. The terrifying implication is that these particles seem to have come from much farther away than the GZK limit should allow. It's as if someone fired a bullet into a dense bank of fog, and it traveled for miles without slowing down or deflecting, arriving with its full force intact. The universe, according to our best physics, should not allow this. The fact that we detect them at all means something is very wrong with our understanding. Faced with this contradiction, scientists have been forced to explore explanations that range from the revolutionary to the truly bizarre. The most conservative approach is to double down on the search for local, hidden accelerators. Perhaps there is a previously unknown type of extreme astrophysical object lurking in our cosmic backyard, a hyper-powerful engine capable of launching these particles on their journey without them having to traverse the vast CMB-filled intergalactic voids. Candidates include nearby active galactic nuclei whose jets are fortuitously pointed our way, or even more exotic objects like gamma-ray bursts or newly theorized magnetized neutron stars with unimaginably strong magnetic fields. The challenge here is that no known object within the GZK horizon seems powerful enough to do the job, pushing us to imagine new classes of celestial powerhouses that have so far escaped our detection. If a local source proves impossible to find, the implications become far more profound, potentially pointing to a failure not of astronomy but of physics itself. The most earth-shattering possibility is that the GZK paradox is our first observational hint that Lorentz invariance is violated at these extreme energies. Lorentz invariance is a cornerstone of Einstein's special relativity. It is the principle that the laws of physics are the same for all observers, regardless of their relative motion. It is this principle that dictates how time dilates and lengths contract at high speeds, and it underpins the entire calculation of the GZK cutoff. If Lorentz invariance is not an exact symmetry of nature, if it breaks down at energies near the Planck scale, then the entire interaction calculation could be wrong. Perhaps at these unbelievable energies, the proton simply doesn't see the CMB photons in the same way, allowing it to travel vast distances unimpeded. This would be a discovery of monumental proportions, providing a direct window into quantum gravity and a realm of physics completely beyond the standard model. Other theoretical resolutions venture even further into the unknown. Some have proposed that these particles are not protons at all, but much heavier atomic nuclei, which have a different interaction cross-section with the CMB. Others have suggested they could be something entirely more exotic, like stable magnetic monopoles or neutrinos with a tiny amount of mass, particles that would hardly notice the CMB and could travel across the universe without losing energy. There's even the speculative idea that our understanding of the CMB itself is incomplete on the largest scales, or that the particles are somehow created much closer to home through the decay of supermassive dark matter particles lurking in the halo of our own galaxy. The GZK paradox represents a beautiful and frustrating collision between particle physics and cosmology. These single, subatomic particles, arriving with the energy of a well-thrown baseball packed into a space 1,000,000,000,000 times smaller than a grain of sand, are messengers from the most violent processes in the universe. They carry encoded information about the limits of our fundamental theories, challenging us to either find their impossibly powerful sources or to courageously rewrite the laws of physics themselves. They are the ultimate high-energy experiment conducted for free by the cosmos, daring us to understand the rules of a game played at energies we can only dream of creating on Earth. Yet perhaps the most staggering proposal of all is the stellar engine itself, a concept that moves beyond simple energy harvesting to planetary-scale manipulation. Imagine a civilization so advanced that it seeks to control not just the output of its star, but the star's very trajectory through the galaxy. A stellar engine or a hexagon thruster would be a colossal parabolic mirror built to harness the star's own radiation pressure. By positioning this mirror to reflect a portion of the star's light, the radiation pressure would create thrust, slowly but surely pushing the entire solar system through space over millions of years. A more complex Class B engine, known as a Kaplan thruster, would act like a giant particle accelerator, using powerful magnetic fields to funnel stellar material into a jet on one side for propulsion, while simultaneously directing a second jet of pure fusion products from the star's opposite pole to maintain the star's stability and prevent it from being pushed into the engine. Such a civilization would essentially turn its home star into a cosmic ark, capable of navigating the galaxy to avoid threats like supernova or to migrate toward richer resources. The detection of such an engine might involve observing a star that is inexplicably accelerating against the galactic tide, or one that exhibits an impossible combination of spectral features and motion, a beacon of a species that has achieved mastery over its celestial environment. The scientific search for these artifacts is not mere speculation. It is an active and rigorous field of study, often operating under the banner of SETI, or the search for extraterrestrial intelligence, but with a focus on its physical rather than communicative manifestations. This branch of inquiry, sometimes called Dysonian SETI, involves sifting through vast astronomical datasets for the technosignatures, the detectable signs of technology that such megastructures would inevitably produce. The primary hunting ground has been the immense archive of light curves from missions like NASA's Kepler Space Telescope, which monitored the brightness of hundreds of thousands of stars for years. Algorithms and citizen scientists scour this data for light curves that defy natural explanation, looking for the telltale signs of partial spheres, swarms, or other irregular transits. Beyond transit surveys, astronomers also search the infrared sky. Any megastructure that captures a star's energy must, according to the laws of thermodynamics, re-radiate that energy as waste heat at longer, mid-infrared wavelengths. A star surrounded by a complete Dyson sphere would be virtually invisible in visible light but would shine brilliantly in the infrared, appearing as a bright, anomalous point source with no corresponding optical counterpart. This search for infrared excess has been a primary tool, with past surveys like ERA's identifying intriguing candidates that were later, upon closer inspection, explained by natural phenomena like distant, dust-shrouded galaxies. This process of investigation and subsequent natural explanation highlights the greatest challenge in this search: the absolute necessity of extraordinary evidence. The history of the alien megastructure hypothesis is littered with exciting candidates that ultimately revealed more about the strange creativity of the universe than the existence of engineers. The most famous example is Boyajian star, which exhibited such bizarre and deep dimming events that even its discoverers cautiously raised the possibility of a partially completed Dyson swarm. The intense worldwide scrutiny that followed, however, ultimately pointed toward a more natural, if still unusual, culprit, a vast, uneven cloud of dust and debris, likely from the breakup of an exocomet or asteroid. Other infrared bright candidates have turned out to be protoplanetary disks, planetary nebulae, or the hot dust from massive asteroid collisions. Each time, a potential technosignature was reclassified as an interesting but natural astrosignature. This does not represent failure, it represents the rigorous application of the scientific method. It teaches us to better understand the myriad ways a star can behave, refining our models and sharpening our criteria for what would truly constitute an inexplicable observation. The enduring mystery, then, is not necessarily the absence of definitive evidence, but the profound ambiguity of that absence. The null result of the search for megastructures forces us to confront the Fermi Paradox with renewed intensity and presents us with two deeply unsettling possibilities. The first is that such structures simply do not exist because technologically advanced, spacefaring civilizations are exceedingly rare or perhaps even non-existent beyond Earth. This is the premise of the Great Filter hypothesis, which suggests that some nearly insurmountable barrier prevents life from progressing to a stage where it can reshape stars. The second, and perhaps more humbling possibility, is that our search is fundamentally naive. Our concepts of megastructures are built upon our own rudimentary understanding of physics and engineering. A civilization millions of years more advanced than us might utilize technologies and principles we cannot yet conceive of, building with materials or manipulating space-time in ways that leave no detectable signature we would recognize. Their artifacts might be all around us, camouflaged as natural phenomena or operating in dimensions we cannot perceive. The silence we hear may not be an empty one, but a silence of misunderstanding, a language of engineering written in a grammar of physics we have not yet learned to read. The search for alien megastructures is ultimately a search for our own future, a mirror held up to humanity's potential, reflecting both our audacious dreams and the profound solitude of our current place in the cosmos. After marveling at the staggering ambition of potential alien megastructures, we are inevitably drawn to a far grander and more humbling construction project, the fate of the entire cosmos, a story written not by intelligence, but by the silent, relentless laws of physics. Our journey through the universe's greatest mysteries culminates with the ultimate question: how does it all end? The answer is not a single foretold destiny, but a spectrum of possibilities, each more awe-inspiring and terrifying than the last, all hinging on the enigmatic nature of the dark energy that already dominates our universe. The leading contender for our cosmic finale is a scenario known as the heat death or the Big Freeze. Picture a universe expanding forever, accelerated by dark energy. Over trillions upon trillions of years, the distance between galaxies grows so vast that the light from one can never reach another. Each island universe, including our own Milky Way, becomes utterly isolated in an ever-cooling, ever-darkening void. Within these galaxies, stars will continue to form for a time, but they are burning through a finite fuel supply. One by one, the stars will flicker out. The massive blue giants will be the first to go, exploding in spectacular supernova. The smaller, longer-lived red dwarfs will cling on for trillions of years, but eventually, even their faint embers will cool to black. The universe will be populated by the stellar corpses, white dwarfs that cool into black dwarfs, neutron stars, and black holes. And then, on timescales so long they defy imagination, even these remnants will begin to evaporate through a process known as Hawking radiation. The universe will approach a state of maximum entropy, a perfect, uniform equilibrium where no energy gradients remain, no work can be done, and no complex processes can occur. It will be a static, silent, and profoundly cold sea of diluted particles and radiation, a twilight that lasts for eternity. This is not an end in fire, but in ice, a slow and quiet fading of all that ever was. However, the heat death relies on the assumption that dark energy is a constant force, perfectly described by Einstein's cosmological constant. But what if it isn't? A more sinister possibility emerges if dark energy is not constant, but actually grows stronger over time. This scenario leads to the most violent end of all, the Big Rip. In this model, the repulsive force of dark energy doesn't just accelerate the expansion of the universe. It eventually overcomes every single force that holds things together. First, the immense scale of the cosmic web would be torn apart, galaxy clusters flying away from each other at speeds beyond comprehension. Then, the expansion would overwhelm the gravitational glue holding individual galaxies together. As the force intensifies, it would rip apart stars from their galaxies. In the final, horrific moments, about an hour before the end of time itself, the expansion would tear planets from their stars. Minutes before the end, it would overcome the forces holding planets and stars together, shredding them into their constituent atoms. In the last fraction of a second, even atomic and nuclear forces would be vanquished, ripping apart molecules, atoms, and even protons and neutrons themselves. The universe would not just end, it would be atomized into a soup of disconnected fundamental particles, unable to ever interact again. The Big Rip is the ultimate cosmic divorce, where the very fabric of spacetime itself is pulled apart at the seams. Beyond these grand cosmological endings lies a threat that is perhaps the most unsettling because of its sheer randomness and speed: vacuum decay. This concept arises from the field of quantum field theory, which suggests that the fundamental fields that permeate all of reality, the Higgs field that gives particles mass, the electromagnetic field, and others, exist in their current state because they are in their lowest possible energy state, their true vacuum. But what if our vacuum is not true but false? What if our universe is merely a stable valley in a much larger energy landscape, but there exists a far deeper valley, a true vacuum, that we simply haven't fallen into yet? A random quantum fluctuation could, at any point in space and time, create a tiny bubble of this true vacuum. This bubble would then expand in all directions at the speed of light. The laws of physics inside this bubble would be completely different. The fundamental constants that allow for atoms, chemistry, and life would be rewritten. As the bubble wall expands, it would obliterate the existing universe, not with energy, but by redefining reality itself. There would be no warning. One moment, the universe would be as it is. The next, a sphere of new, alien physics would be expanding at light speed, and by the time you could see it coming, it would already be upon you. This is not an end from within the system, but a crash of the entire system, a spontaneous and total rewriting of the cosmic rulebook. Each of these potential destinies is dictated by the properties of dark energy, a force whose true nature remains one of physics' greatest secrets. Is its strength truly constant, leading to the long twilight of the heat death? Or is it dynamic, a field called quintessence that could intensify and bring about the Big Rip? The answer lies in precisely measuring the equation of state of dark energy, represented by the parameter W. A value of exactly -1 indicates a constant cosmological constant. A value more negative than -1 points toward phantom dark energy and a future Big Rip. Current observations are incredibly precise, but they still allow for a small range of possibilities. Every new telescope and sky survey, like those from the Vera C, Rubin Observatory and the Nancy Grace Roman Space Telescope, is designed to measure the expansion history of the universe with ever greater fidelity, hoping to pin down this number and finally tell us which story we are in. Contemplating these ends is not an exercise in nihilism, but a profound act of connection. The same cosmic evolution that forged hydrogen in the Big Bang fused heavier elements in stellar furnaces, and scattered them across space in supernova explosions to eventually form our planet and ourselves, is also the process that dictates our ultimate fate. We are not just observers of the cosmos, we are a temporary manifestation of it, a fleeting pattern of stardust that has become conscious enough to trace its own origin and project its own end. Understanding these distant futures helps us understand the universe we live in today, the forces that shape it, and our own incredible improbability within it. Our cosmic destiny, written in the invisible ink of dark energy, remains the final, great unsolved mystery, a reminder that the story of the universe is still being written, and we are here for a brief and glorious moment to read its pages. And so our journey through the cosmos's greatest enigmas comes to a close, yet the true wonder lies in the realization that this is not an ending but a starting point. We've ventured from the profound silence of the Fermi Paradox to the ghostly tug of the Great Attractor. We've grappled with the invisible dominance of dark matter and the repulsive force of dark energy. We've stood in awe of the fleeting brilliance of fast radio bursts and the enduring, perfect geometry of Saturn's hexagon. We've chased the whispers of Martian methane and the ghost of a planet that may lurk in our own solar system's frozen fringe. Each of these 25 mysteries is a testament not to our ignorance, but to our boundless curiosity, a beacon illuminating the vast, uncharted territories that still lie before us. What makes these puzzles so captivating is that they are not mere gaps in a map waiting to be filled. They are profound challenges to our very understanding of reality. They force us to question the laws of physics, to invent new technologies, and to imagine possibilities beyond our current comprehension. The universe is not a static museum exhibit to be passively observed. It is a dynamic, evolving riddle, and we are the detectives, armed with mathematics and imagination, piecing together a story of unimaginable scale and complexity. Every unanswered question is an invitation, a call to the next generation of scientists, engineers, and dreamers to look up at the stars and ask, what if? Now we turn the question over to you. Which of these cosmic conundrums captures your imagination the most? Does the eerie silence of the wow signal send a shiver down your spine? Are you drawn to the terrifying implications of vacuum decay, or the beautiful, impossible structure of the Red Rectangle Nebula? Let us know in the comments below. We are endlessly fascinated by which mysteries resonate most deeply with fellow explorers. If this journey through the unknown has sparked your sense of wonder, you're in the right place. We are dedicated to diving deep into space's greatest enigmas, unraveling the science and the stories behind the headlines. For more content that explores the furthest frontiers of knowledge, be sure to subscribe and hit the notification bell so you never miss an adventure. The universe is holding its secrets close, but together we can begin to pull